Greetings, everyone. Good morning, good evening, good afternoon. There's folks who are pretty much all over the world joining us today. Welcome to the final Summer Research Symposium. I'm very excited to see all you folks coming together for exciting presentation. We'll be recording these sessions. If you miss something, you can come back to them. We'll share the recordings. But let me start off by first saying thank you and congratulations to you students, but also to the mentors and all the supporters. Many folks have helped us through the summer to make this program what it is, what it has become. And it would not have been possible with all your help. So thank you so much. And again, big congrats to the students. You all worked really hard and we're excited to see what you're going to present today. We had this year 3 cohorts that we're combining today into this summer symposium. We had the National Science Foundation funded research experience for undergraduate site. Computational modeling serving Portland. We had 8 students in that site. We had the alternative research experience for undergraduate program to design, program, and use computers to benefit society. We had 38 students in that program. And then in my own lab, we had 12 students. So there's a lot of folks this summer doing amazing work. And once again, we're excited to see you all present today. The NSF leadership team was myself, Jay, who is online as well, and Yogeshwar. He's a grad student. He was running many meetings and was running the show and helping students to be successful. And also Nadine, who is the official NSF program administrator. For the altREU program, that was mainly run by myself and Yogeshwar. And then my lab students, that's mainly run by myself. Good. So again, thanks to all the mentors who helped students to be successful. We have over the summer worked on an exciting other project that is completely led and driven by students. We call it the Summer Proceeding. So every student was invited to submit a chapter to a book, to a proceedings that we will self-publish on Amazon at the end of the summer in about a week or 2, hopefully. The draft deadline is today, I think, and that's a good reminder as well for you folks. If you haven't submitted your draft chapters yet, today is the day. And so you'll be able to get that these summer proceedings on Amazon. We'll also offer them for free as a PDF. But this was, I think, a great opportunity for students to get something published in the form that is citable, and hopefully that will have an impact on your resumes. But also, it could be a nice draft for an actual journal or conference publication later. Anyway, so keep an eye out for more news about that. Again, this was driven by students, and the proceedings were edited and put together by students. Good. So we have a pretty full slate today. We have 4 sessions with different breaks in between. We spread things out quite a bit to account for all your different time zones you're in. And so we have a variety of breaks in between. I posted the link to the spreadsheet. That's the updated version of the program. The presentations are what we call Ignite style. That's a well-known style to present. 5 minutes, 20 slides. Each slide auto advances with 15 seconds with a 15-second timer. So it's quick and short and sweet. It's nice for the audience because the presentations are short. And it needs some good preparations from the students. And I've seen some practice runs already that were very exciting. So that's what we're going to do today. We'll try to stay on program and on schedule as much as we can. And there's 5 minutes for each presentation and 2 minutes for questions. And I would invite everybody to ask questions at the end of each presentation. All right, without saying more, let me unshare here and let's get started with Shani and Bari. You're going to be the first presenter. Let me see. You should be able to share your screen. All right, it's coming up. Is your sound working?
Yeah, can you hear me?
Yeah, we can hear you. Yeah, perfect. Yeah. All right, whenever you're ready.
1 second. Usually I auto advance it at this point, but I can't see the button for it.
If it's Google Slides, it's at the bottom left.
Yeah, I can't see it. Oh, okay. Hold on. Let me stop share really quick. Sorry.
We will keep the Zoom meeting going. If you want to hop off and come back, you can do that. We'll keep it going during the breaks as well, so you won't get disconnected.
Okay, yeah, I am not manually do it. Sorry about that. So sorry.
Is it Google Slides?
Yeah, just once I get onto like escape and do it.
Okay. Yeah, do it manually
Okay, sorry
in
about that.
that case, yeah.
Okay.
All
Hi
right.
everyone, my name is Shini Ambari and I'm a part of the altREU program led by Dr. Teuscher. And today I'll be discussing the project I've worked on for the duration of the summer titled Orphan Drug Trials Forecasting Phase 3 Clinical Trial Success. So, to give some background about orphan drugs, these are a class of pharmaceuticals that target rare diseases, which are diseases that affect very low patient populations. And because of that, historically, there's been low financial incentive for companies to make medications for these groups of people. So, to combat this, Congress passed the Orphan Drug Act of 1983, which gave many financial incentives for pharmaceutical companies, most significant being a 7-year market exclusivity period. Additionally, to reach orphan drug designation, the drug has to match a specific disease. So my project focuses on predicting the outcome of historic phase 3 clinical trials that use orphan drugs. And I wanted to do this looking exclusively at trial variables such as enrollment, duration, and sponsor, in addition to other variables, and not look at all at the medical impact. And how I did this was by creating a random forest model that would either classify a trial as completed or terminated. Additionally, I want to look at key variables that correlate with trial success. So how I did this was I first went to the FDA Orphan Drug Designations and Approval database, and I got a comprehensive list of all designated and approved orphan drugs, and I isolated the approved drugs, which are ones that are currently on the market. I wanted to find the trial that they were initially used in, so I aligned the sponsor, indication, in the intervention, which is the company, the condition, and the drug for each trial to ensure that each trial was an orphan drug when the drug was being used. Next, from there, I got 50 completed trials and 28 terminated trials, and then I extracted information from each trial to use as my variables of interest. So I got information about the study design, information about the success of the sponsor and how many approved drugs they have, in addition to other miscellaneous variables such as the duration, the enrollment, and a collaborator. Many of these variables have been vetted by previous researchers as key trial variables, and all of this was done to classify each trial as either completed or terminated. Next, I created my model, which was a random forest using 5 folds of cross-validation, and then I needed to adjust for the class weight, and then further tune the model, and finally do a feature importance analysis. The metrics that I used for this were accuracy, precision, recall, F1, and ROC AUC, the latter being the most important for this project because it plots the true positive rate against the false positive rate, essentially the model's ability to classify a positive from a negative. First, I did a class weight adjustment assessment, and I compared 4 different class weight values, and I saw there was not a big significance between them, so I decided to just select one of these models and continue forward for further hyperparameter tuning. So here I used Grid Search CV to optimize the metric ROC AUC, and once again, I found that there wasn't a significant difference when I did this tuning, likely due to lower amounts of data. Finally, I did a feature importance analysis where the model looks at the variables inputted and gives a weighted value of how relevant each one was for the classification of either completed or terminated. And here you can see that the duration was most relevant, followed by the enrollment, and finally the success ratio of the sponsor. So overall, the metrics that I found were all around 80%, which I would say gives a little bit of preliminary evidence that you can make predictions on phase 3 orphan drug trials based on just the trial variables, not looking at all on the drug design or the medical analysis. And additionally, we found that the duration and the enrollment were the most significant variables that led to trial success. And I think all of these findings, by focusing on the trial variables themselves, just show the vitality of having quality trial design and execution, and that companies should really allocate a lot of information and a lot of time to preparing for the trials because it's very reflective of how the trials will go themselves. Additionally, the ROC score that I got was consistent with previous works, which is another positive signal that these can be like preliminary findings. And finally, if I was to continue this project, I would definitely want to use much larger amounts of data. That was a big constraint of this project, and also integrate active trials to which could give like real-time insights for pharmaceutical companies that are looking to optimize like investing in trials and resource allocation. And additionally, because clinical trials for orphan drugs is like very specific, I wanted to incorporate economic variables, which I eventually did not get to, but I think that would be a great way to continue this project. And special thanks to Dr. Teuscher, Dr. Leipor, Dr. Macy, and Yogeshwar for all your support. I really enjoyed this project and working with you all. So thank you so much.
Thank you. That's a great start. Good. Any questions from the audience? You can also put them in the chat. Why random forests?
That's what I was basing it off of one previous paper that they said random forest was the best.
Okay. And were you able to compare with that paper? That was my other question with regards to related work. Has anybody else done what you've done, and did you compare with that work?
Yeah, so their work, the main paper that I was looking at was they use a lot of different like types of diseases, not just rare diseases, and then they also looked at both drug information and trial information. And
Okay.
I haven't compared them too much yet as a result, but I did see that the ROCs like were in line, which I thought was a good sign.
Okay, that's great. Yeah, thank you. Thank you. Awesome. Any other questions from the audience? All right. Thank you again. Great work. And I hope you will continue this. There's lots of room for more work, as always, with research. Great. All right. Next up, Simran and Tanisha. Okay, we see your slides. Great.
Great. Tanisha, are you ready to start right now?
Yes.
Okay, great.
Okay. Whenever you're ready. Yeah. Good.
Hi, my name is Simran.
My name is Tanisha.
And this is our project titled Development of Biosensor-Based Lie Detection Technology.
To give an introduction to the lie detector, they're used in the security industry and widely used despite not being accurate at detecting deception, as shown here with the United Kingdom police forces increasing their usage of it as it's the only known parameter. This is mainly due to no widely acceptable alternative as a reliable method of detecting deception, and lie detectors being used as supplementary tools. In this project, we are not focused on increasing the accuracy of the lie detector, but rather investigating and experimenting with repurposing biosensors to detect body language changes. And as you can see in the picture shown, that's what our graphs give. The key objective of building a lie detector prototype to trigger these sensors can be broken down to how it will identify behavioral changes, have manageable instructions, and inform the user of results instantly. This is a prototype that we've designed of the lie detector on tlab that includes areas to place our various sensors.
The inner workings of the lie detector in the circuit diagram includes an Arduino Uno, which is connected to two sensors, a galvanic skin sensor and a heart rate sensor, along with an LCD screen and 3 LEDs, and all of these connections are powered using a 9-volt battery.
This is a constructed lie detector which features the sensors, display screen, LEDs, and on and off switch. The lie detector is housed in laser cut black acrylic, which we then assembled, as you can see. The prototype includes a heart rate sensor, which only measures the amount of IR red reflected by the user's finger, and that's the parameter for the polygraph and for further testing. Additionally, it also includes a galvanic skin sensor, which was repurposed as a muscle sensor based on preliminary findings and better accuracy. Then to relay information to the user, it features an LCD screen and LCDs to show truth, liar, unknown reading. As you can see, we have red, green, and yellow for the same purposes.
In the Arduino code, the lie detector starts by displaying instructions to the user, followed by examples of what each of the 3 LEDs mean, and it begins by measuring the baseline readings of the two sensors. On the left here, this is what describes a lie in the code, where we set thresholds for the sensors, and the prototype communicates with the proper LED colors, and it takes in a new baseline reading before continuing to analyze real-time signals. And on the right here is what describes an unknown reading, where one of the sensors meets the threshold and the other does not, and it follows the same process of establishing a new baseline before analyzing real-time signals. The initial testing of the lie detector shows a truth, lie, and unknown reading in that order, where the LEDs show a change is detected, and a lie is when the red and orange LEDs are turned on, and the unknown reading is where just the red is turned on. For the infrared sensor, we saw a trend that as the pointer finger moved away from the sensor, the amount of reflected infrared light decreased, which is we were able to set our first threshold on. And then for the galvanic skin sensor, by setting a relatively low threshold, we saw false triggers appearing before the actual change, which can lead to false positives in our data collection. And by testing a very high threshold meant that the trigger would have to be very dramatic to signal a change, but we wanted a less aggressive trigger. So in testing a threshold between the two extremes, we found a threshold where we were able to see detected change and returning shortly back to baseline before detecting another change shortly after. For future design considerations, we are interested in using a renewable battery to optimize the efficiency of the lie detector and developing a more robust algorithm to account for multiple sensors being used at the same time. Thank you so much for listening to our talk.
Thank you.
Thank you. All right, questions from the audience? Did you test things with yourself, or did you have a population of test subjects, or how did that work? How did you get your data actually?
So as for right now, we just tested it on both of us to see how exactly the signal worked. And for the galvanic skin sensor especially, to repurpose it as a muscle sensor, we ended up using like a oscilloscope to check the signal of it. So it was really just a collection between us, but in the future, we're open to using for a wide range of different populations.
Okay. And how reliable was it?
So the reliability in terms of accuracy, I can't really speak on too much since we're not really looking for accuracy as much. But as for how the sensors work and relaying information, the results were very instant. So I would say it was pretty reliable in terms of signaling the results to the user and the sensors working as they were supposed to in the whole electrical connections.
Okay. Did you think about other sensors, and if so, what would they be?
We were
So
one of the main ones. I'm sorry.
no, Tanisha, you can go ahead.
Yeah, one of the main ones actually was a heart rate monitor, as that's a really good indication. But then
Okay.
again, like an oximeter or a pulse meter, but then to repurpose it into something as simple as incorporating it into the neural network would have been a little harder. And especially because it's galvanic skin sensor, it was more easier to use and repurpose, that's why we went with it.
Yeah, yeah. Okay. Very cool. Yeah, it's great that you have a prototype that you can play with. Awesome work. Thank you. All right, let's move on to Alina.
Yes. Let me just share my screen. Okay.
Perfect.
Okay. Hi, everyone. My name is Alina Dashapitala, and I was a high school intern in the teuscher lab this summer. And my project explores a CNN-based approach for resume screening purposes. So what's the problem? So resume screening is a crucial step in the hiring process, yet it's often time-consuming and prone to human bias, which is why many companies and industries have begun to adopt ATS scanners or similar technology to automate these processes. And my project aims to understand how this process looks using a CNN-based approach. So this was the final goal of my project, a simple front end, a simple UI that would take in a resume and analyze it for industry suitability, predicting the industry that a resume is most suited for based on keyword prevalence. But how did I get here? And why this project? I came into this internship wanting to learn more about large language models and about how data and large amounts of information can be processed and adapted to automate or solve a task in industry, and CNNs provided a great foundation for me as a beginner. So what are CNNs? Convolutional neural networks, also called CNNs or convnets, are deep learning algorithms designed to assess images and assign importance to different parts of the image with the primary goal of analyzing and identifying patterns. Why CNNs? As I mentioned, historically CNNs have been used for image-based tasks, but after reading papers such as the ones on these slides, I became interested to learn how the model might actually be well adapted to text analysis as a result of the CNN's ability to recognize patterns in a unique way. So step one of my project was collecting the data. I used a data set of 2,000 plus resumes from 30 industries on Kaggle, each labeled according to their job category. And this provided a solid foundation for both training and also evaluating my model. Once I collected data, I had to prepare it for later visualization and then also feeding it into my model. I removed stop words like pronouns and articles, and then also cleaned the text by removing punctuation. And then I used lemmatization to reduce words to their root form. Many pronouns or words without specificity to an industry were removed from the data.
Using word clouds, I visualize the most frequent terms in each job category. Word clouds are images where the larger words are the ones which appear more frequently in the text. These visualizations helped identify the keywords that the CNN would later use to classify resumes. I used term frequency, inverse document frequency, which assigns numbers to words with more frequency. And then I also incorporated bigram and trigram specificity into the word clouds so that skills with more than one word would be accounted for, such as information technology showing up as two words instead of just information. This is my project pipeline, which involves pre-processing data to generate word clouds and then training the CNN for classification, which is then integrated into the front-end application where users can actually upload their own resumes. My CNN architecture includes an input layer, multiple convolutional layers to capture features, dense layers that process these features, and an output layer that classifies the resumes. In my CNN, the convolutional layers extract key features from the resume text by detecting patterns and relationships between words. These features are then processed by dense layers, which classify the resumes into specific job categories based on the extracted text. To optimize the model, I used Optuna for hyperparameter tuning. Running 100 trials helped me explore a wide range of configurations such as optimizer type, epoch size, and others, improving the model performance. Initially, as you see here, I used a manual approach for early experimenting with various hyperparameters, but this proved to be pretty time-consuming and inefficient for me, so using Optuna helped to automate this process and allowed me to test a wide range of hyperparameters to achieve the best model accuracy. This model was trained on a split of training, testing, and validation data. I implemented early stopping and patience functions to ensure that my model wouldn't continue to train if it wasn't performing well on a certain set of hyperparameters. This helped me save time and also increased efficiency. Here's the final model results, which show an improvement in accuracy and loss, but still has room for growth. In terms of model metrics, you can see that accuracy and loss are generally correlated between the training and testing sets, but there's a pattern where the training set tends to perform a little bit better, indicating some minimal overfitting. To achieve more accurate results, I plan to train the model on more data in the future. So going back to the final product, here's my final product, and you can see an example of the model predicting an industry which my resume is most suitable for, which I tested out for the purposes of my project. And in terms of improvements and further development, looking forward, I plan to incorporate contextual embeddings or transformers like BERT to help my project be more adapted to multilingual resumes, perhaps. I also would like to account for more industries, train my model on more data, increase the aesthetics and usability of the UI itself, and then also account for soft skills and not just hard skills. So in conclusion, this summer I worked on a convolutional neural network-based approach for resume analysis. Thank you so much for listening to my presentation. Thank you to Dr. Teuscher for his mentorship in my project, all the interns in the lab, and yeah, if anyone has any questions, I'm happy to answer. Thank you so much.
Thank you. Questions? Nora is asking, why did you choose to do convolutional neural networks versus another type of neural network? Why CNNs?
Yeah, so initially when I came into the project, I was kind of interested in just large language models itself, but wasn't really sure how to go about that. And I thought actually Dr. Teuscher recommended creating a CNN, which would be a good foundation as a beginner. And I found it really interesting because I was reading, like in the papers that I showed, that sometimes when you have to understand or do text analysis, there's a lot more importance on the context surrounding the word, which is maybe not the same for images. The image analysis is a little bit different, but there are some similarities between image-based analysis and text-based analysis. So I thought it would be cool to try something traditionally used for images on text and see if it could still produce accurate results, which it did. So that was to explore.
Excellent, thank you.
Thank you.
Are you planning to make the tool available publicly?
Yes, I am. I actually just wrote about that in my paper too, but I would like to eventually improve the aesthetics and usability of the UI and make it accessible. So then I can also train the model on the resumes that are uploaded through it. So
okay, great.
Okay, thank you.
Awesome. Thank you so much. Good. I don't see any other questions, so let's move on to Nora.
Can you see everything all right?
We can see your slides. Yeah, coming up. Yeah.
Hi, my name is Eleanor Isles. I'm a high schooler from Portland, Oregon, and today I'll be talking about the cyberbullying detection model that I made. I'll talk about what cyberbullying is, why models like this are needed, how this model is made, and what this model does. So what is bullying? Bullying is essentially when someone seeks to harm, intimidate, or coerce a different person. There are 5 types of bullying: physical, verbal, social, sexual, and prejudicial. However, along with the technological revolution, a new type of bullying has come to light, and that's cyberbullying. Cyberbullying is another form of bullying that takes place online. A key difference with cyberbullying is how the effects of cyberbullying are invisible to perpetrators, so they may not fully grasp the consequences of their actions, which is referred to as the disinhibition effect. 30% of teens have been cyberbullied in their life, 13% in the past 30 days, and 15% have cyberbullied others. Furthermore, 15% of tweens have been cyberbullied in their lives. So it's a problem, but how do we fix it? That brings us to this project. The goal was to contribute to ongoing efforts to prevent cyberbullying. So how does one do that? They do that by detecting cyberbullying within text, among other methods. But that's the method that I chose. Well, there are many methods to prevent cyberbullying, from education on how to responsibly use the internet to manual moderators, so they click and say this is cyberbullying, to keyword filtration. But there also is a different method that I chose for this, which is supervised machine learning. So why is that the best option? Well, cyberbullying is really intricate, to say the least. You can't just flag some words and make it all go away. And supervised machine learning methods are useful in recognizing those intricate patterns to determine whether a given statement is cyberbullying. So how did I make this model? Well, the first step I took was finding a data set. This CSV data set from Menly data that I chose had binary labels and messages that were sourced from text and not tweets or reviews, which is ideal for this model because it's supposed to be designed towards detecting text cyberbullying. Next, the data needed to be prepared and processed. It is extracted from the CSV file and read into a pandas data frame. The blank rows from the data set were removed, the characters became lowercase, and the special characters were also removed. Then the stop words, which are words that aren't useful in helping the algorithm, were removed. And using the NLTK library, the words left were lemmatized, which is converting them to their base form. Then it was all vectorized using count vectorizer, which essentially turns the words into numbers, aka vectors. The data was set up and organized into 3 categories: training, which has the most data, validation and testing for the accuracy to be best gauge. Matplotlib was also used to construct a graph to show the predicted probability and set up the confusion matrices. And the data, well then in order to train the data, you need a model. So when choosing a supervised machine learning model, I gathered multiple that I thought might suit the purpose and tested them on accuracy. In the end, logistic regression was the most accurate. Additionally, an input field was developed in VS Code for users to enter a statement for analysis. The statement is a pre-processed before going through the model and then comes out as a binary output, 0 for not cyberbullying, 1 for cyberbullying. After being ran, the model fed back some statistics about its accuracy. The main piece of information that was the most useful was for the testing data. The overall accuracy came out to 86%, showing promise in its capability to detect cyberbullying. Furthermore, the precision when it came to the cyberbullying data was 84% and the recall was 72%. And when it was not cyberbullying, the precision was 87% and the recall was 93%. So the data was a little more confident when it wasn't cyberbullying. Here's also a test confusion matrix to show the accuracy. 0 is not cyberbullying and 1 is. You can see the distribution of the false negatives, false positives, true negatives, and true positives. And then there's also, you're going to see in a minute, the predicted probability distribution graph. And this shows the likelihood of whether a given statement is cyberbullying. It's color-coded about whether it actually is or not. And this allowed for creation of predicted probability for both the testing and validation data sets. And this graph displays the frequency of statements. So based off of how much data was inputted into the model, there was a different amount of accuracy. For 1,000 words, it was 79%, 10,000 was 83%, and 90,000 was 86%, but you could see the graph was more logarithmic. In conclusion, this model was able to reach the goal of being able to detect cyberbullying, and it has potential to be applied in areas where it can prevent cyberbullying and create a safer online environment by being integrated into platforms to provide instant feedback on harmful content. So what's next? Some next steps for this model include integrating, improving, and implementing. By that, I mean integrating it in a place where people could use it, improving the accuracy, and implementing a continuous learning mechanisms to keep it up to date. Thank you so much to everyone who helped me with this project. Do you have any questions?
Thank you. Questions for Nora?
I can ask a question. So you mentioned that you wanted to use logistic regression, but I was wondering if you decide to develop the project further, would you still continue using logistic regression, or do you think you would use another type of model?
I think I'd want to try out different types of model and look and see which one has the best accuracy and like compare the different versions of which models are best for which aspects of cyberbullying detection.
Great. Could your pipeline be used for other data sets or problems?
Yes, it should be able to. Currently, I'm trying to work to get it equated to a spam data set so it can detect whether something is spam or not. But this, the setup of it should be able to work with other data sets as well and other problems.
Great. All right, thank you. Okay, we're going to move on to Aparna. Thank you again, Nora. Aparna.
Okay, can you guys hear me?
Yeah, we can see the slides and we can hear you.
Great. Hi, everyone. My name is Aparna, and my project is the prediction of suicide rates across the U.S. using healthcare access data. Suicide is the most destructive silent killer of our time with no clear cause or cure. However, it has been found that various mental health issues, such as depression, are strongly connected to suicide incidents. So the only way to take action to help this problem is care that can contribute to the well-being of those struggling with these disorders. However, 83 million people are living with no access to a primary care physician. Medicines and therapy required in the care of disorders such as these bear costs of multiple thousands of dollars. If a relationship between suicide incidents and healthcare access can be shown, steps towards solving this problem can be taken. The objective of this project is to use correlations between healthcare access data and suicide incidents in America to predict suicide rates. Accurate predictions would show that this healthcare data has an influence on suicide rates. Most previous work has focused on gathering materials from electronic health records and classifying by susceptibility, rather than the public health approach I'm using. Data on suicide rates, number of primary care providers, mental health providers, uninsured individuals, individuals with dedicated health providers, and those who are avoiding care due to the cost was collected using the CDC and America's Health Rankings. However, before I began, I found that some of the data I had collected had data where states were missing. To resolve this issue, a k-nearest neighbors algorithm was used to fill in the data. For example, if Oregon had missing data, the program worked by using the 3 values that were the shortest Euclidean distance away from the missing value. So in this example, that would be data from California, Idaho, and Washington. Before I explain the process of data analysis, I would like to mention a metric that was used throughout this project. The CDC organizes the country into 9 regions, which I converted into numbers from 1 through 9 and used throughout my project to help model the data easily. The first step after collating this data was to create simple facet scatter plots using Plotly. These scatter plots help to visualize the large group of data used and choose what model would be best. Through these scatter plots, a correlation between the factors chosen and suicide rates can be seen, allowing me to choose the correct models. I decided on 2 models for this project. The first one was a linear regression model, which predicts a dependent variable based on multiple independent variables. This model structure involves an intercept, coefficients for each feature, and an error term. The second model I decided was on a long short-term memory model, which is a type of recurrent neural network. It is useful in time series forecasting when predicting for future events using past trends. It consists of a cell state that allows info to flow across time steps, a forget gate, an input gate, and an output gate. After deciding to focus on these two models, I continued my data analysis. However, now I use the criteria for using a linear regression model to guide the statistical models I created. The first criteria were that variables being used in the analysis have a direct linear relationship. So I turned back to the scatter plots and found that a relative linear relationship could be found between the factors, which allowed me to continue. The next criteria was that the data followed a normal distribution. As seen in this histogram, this was valid. The next criteria was to take a more detailed look at the correlations and ensure that the direction was as expected. For example, as the number of physicians went down, the suicide rate should increase. A heat map was made for this purpose, and the direction of correlations was confirmed. For the linear regression model, the state names were converted using integer encoding. Then a training set consisting of 2017 and 2018 data and a testing set consisting of 2019 and 2020 data was made. The stats model package of Python was used to evaluate model parameters. For the LSTM, it was created using a supervised learning problem. The number of physicians, mental health providers, uninsured, avoiding care, people with the dedicated health provider, the region, and the suicide rate in 2020 was used to predict the suicide rate in 2021. The data set was split into a train and test set, which is the same as what was used in the linear regression. The stats model package outputs an OLS regression result, which evaluates the model parameters. As you can see, the R-squared score of this example is 0.39, which is much lower than the perfect fit benchmark of 1. In addition, the p-values for 4 out of 7 of the variables are greater than the alpha benchmark of 0.05. Unfortunately, this showed that the linear relationship between these variables was not significant enough to continue using this model. So this model was not used to make predictions. However, the LSTM did converge. So it was used to make predictions with a final RMSE of 4.459. This is an example of how the results were formatted. Now, as this graph shows, while not all predictions were perfect, enough of states within each region were accurate to show a strong correlation between factors and rates. They have an impact on suicide incidents. The results of this research show the power of preventative care. With the concrete evidence these accurate predictions provide, efforts can be made to raise the number of health professionals in shortage areas. In addition, this can also provide the basis for a new area of healthcare to be invested in, ensuring every patient has a dedicated health provider attached to them to provide care when needed. There were some concerns involved in this project. The biggest was the size of the data set. It was extremely small because the number of mental health providers were never included in healthcare data sets until the year 2017, greatly limiting the amount of data I had to use. In addition, data relating to issues such as suicide are not uniformly reported across the country, with each institution choosing their own metric, which makes data difficult to analyze. Some of the next steps would be adding more indicators to see if predictions can get more accurate. I could add pharmacy density in certain areas, which I'm currently trying to do, or the number of designated hospitals or medical healthcare facilities in an area. Another step could be narrowing predictions to counties or states where suicide incidents have been found to be high. Thank you for listening.
Thank you. Questions from the audience? On your data analysis slide, it looked like the Pacific was quite an outlier if I decoded the color correctly. Do you have an idea why that is?
I'm not fully sure. Those are one of the things I wanted to analyze, like with my results, trying to look for more of a connection between the region and the location. So that would also be part of my next step. So any outliers that I found could be investigated more deeply. I could narrow in my analysis to kind of see Pacific. In addition, I also found that the Midwest regions, states such as Wisconsin, had extremely high suicide rates. So maybe investigating that state more deeply would help to like find more correlation.
Yeah. Okay, yeah, that's a good idea, yeah. Great, thank you. Any more questions? Good. If not, we're gonna move on to Paula.
Yes, I'm going to share my screen.
Or
Okay. Can you see it?
yep, looks good.
Okay, perfect.
We can see you and we can hear you. Good, whenever you're ready.
Okay. Well, hello, my name is Paula, for those who don't know me. And today I'm going to be presenting my research project that I did with my mentors, which was multilingual misinformation in artificial intelligence. Okay. So what is artificial intelligence and large language models? Artificial intelligence is technology designed to stimulate human intelligence, while large language models, or LLMs, are AI systems trained on base text data that are capable of generating human-like text. Students from all walks of life all over the world use LLMs as a way to find accurate information quicker. Detecting misinformation across languages is critical because it ensures the integrity and accuracy of information. Misinformation can influence public opinions and global decision-making on a much global scale. So for this research project, we utilized OpenAI's GPT-4 model due to its increasing popularity among students from all walks of life. Our three main objectives for this research project was tone preservation, misinformation detection, and multilingual approaches. We utilized two distinct datasets. The correct news dataset consists of authentic news articles from reliable sources, while the incorrect news datasets contains fabricated stories. And the languages that are included in those datasets are English, Spanish, French, German, Italian, Portuguese, and Chinese. Our data collection process starts by selecting it selects the articles first, then it translates those articles using the LLM, then it integrates those articles into the data set, and then the analysis should be ready for the articles. Our methodology overview. So first we start by loading the environment variables using load do t and v parentheses. Then we set up OpenAI client with API key. We load the fake news dataset from a CSV file, and we also load a true news dataset from another CSV file. Then we analyze those articles for each dataset. Then it detects the language and translates the text. It accesses the misinformation, and then it prints the results. A custom function utilizing OpenAI's GPT-4 model was developed to detect the language of articles and translate them into English, aiming to preserve the original tone and content. This function interacts with the GPT-4 API, providing outputs of both detected language and translated text. The translations results using GPT-4 showed that while the integrity of original content was generally maintained, some subtle tonal shifts were noted. The results for language detection and translation show that the GPT-4 model successfully identified the languages of the articles and translated them with high accuracy across multiple languages. So in this table, we have the languages used for the two datasets. Then we have the articles that are detected and the translation quality using the blue score method. The GPT-4 model also showed robust accuracy in English, but less consistency in non-English languages. Misinformation detection rates were highest in English, with a notable decrease in accuracy for languages like German, Portuguese, and Chinese. So this is the function, or better said, the math equation that we use to detect the accuracy for this table specifically. So it has the same languages because we use the same languages for both data sets. We have the true positives, the false positive, and then the detection accuracy. In here, you can see that the German scored 50, the Portuguese scored 50, and the Chinese also scored 50 in accuracy. The study faced challenges with translation artifacts and model inconsistencies. Translation errors such as shifts in tone or loss of nuanced meanings occasionally skewed misinformation assessments, especially in complex languages. The findings highlight the need for AI models for better handle multilingual content and misinformation detection, suggesting that future models should focus on improving translation accuracy and consistency across diverse languages. Future studies could focus on exploring bias mitigation in training datasets and developing collaborative AI models that integrate human feedback could also further refine translation accuracy and misinformation detection, ensuring more equitable and effective multilingual support. Some key takeaways were that firstly, while LLMs like GPT-4 typically maintain the integrity of translated content, they can introduce subtle shifts in tone, indicating a need for improved accuracy in translations. Secondly, the model showed strong performance in detecting misinformation in English, but its effectiveness varied significantly across non-English languages, highlighting the necessity for enhanced multilingual detection capabilities. These findings suggest substantial opportunities for future enhancements, including better training methodologies, bias reduction, and the integration of cross-lingual learning strategies to better support diverse linguistic environments. Thank you so much for your attention on my project.
Thank you, Paula. Questions from the audience? Did you compare with other large language models?
Specifically, no. I only, for this project, specifically only used ChatGPT because it was the most used for students. So I wanted to represent a data more based for students.
Okay, yeah, okay, that makes sense, yeah. But would you expect large differences between another model and ChatGPT or
Yeah.
GPT-4?
Yes, so for a future project, I would like to try Gemini because it's also a famously used LLM model for students. And I believe that will also change because Google is more vast in information compared to ChatGPT, which is recently new technology. Gemini is also new technology as well, but it uses Google's database up to date compared to ChatGPT.
Okay, great, yeah, thank you. Good, other questions? All right, if not, we'll move on to Theo. Theo, are you online?
Yeah.
You are.
Oh.
Okay.
And then I have to set it to auto advance.
Yep. Good. Looks good.
Okay. So my project, along with my partner Brian, who's not here today, unfortunately, is Ecostate Networks for Expressive Music Performance. This was our internship project for the teuscher lab summer project. So we have to talk about expressive music performance. We have to talk about how music is written in the first place. It's in the form of sheet music. You can see an example on screen. Each dot on the page represents a note and some limited information about that note, how long it should be held, for example. Expressive music means the phrasing introduced into the music by its performer in order to convey emotion or feeling. To do this, the musician makes hundreds of adjustments to the loudness and duration of notes that aren't explicitly notated in the sheet music. Those adjustments in total add up to what you might call the human element of musical performance. For this project, we focused on one aspect that humans change from the written music, the velocity. Velocity, also known as loudness, refers to how loud each individual note is played. If I was to play the music on page, I'd be making these velocity adjustments myself intuitively. And the idea of this project is to train a computer to make these adjustments to emulate that expressive human element completely automatically without human intervention. So, how do computers play music in general? A computer will start with sheet music, turn it into a MIDI file, you don't need to worry about that step, and then turn it into audio we can listen to. And both those steps have already been robustly described by other people and are kind of consistently done in the same way. However, the final product using just that step will sound inhuman. And any musician listening will hear the lack of expression. So what we need is an extra step, shown by this green arrow, that changes the velocity of each note to sound more human. So let's talk about what that green arrow could be. It could be a rule-based system like the KTH rule system, which uses human-described rules to control the velocity based on preset signals in the music, but it requires a lot of human intervention to set up the rules and can still sound computery. Other people have proposed a feed-forward neural network, which is the most basic type of neural network, and can produce results similar to the KTH system with less human intervention, but humans still struggle to tell the difference between these results and the computery unmodified results. Finally, you have linear basis models, which define so-called basis functions that first identify structural aspects of the piece and then train on those structures. But these models struggle to tackle complicated time series like a full piece of music. So, is there another way? Maybe we'll go over what we propose in this project, which is a type of model that hasn't yet been applied to the problem, called an echo state network. So first we'll describe what an echo state network is. An echo state network is made of three parts: an input layer, a reservoir layer, just a reservoir, and an output layer. And the input layer is what's going to take in certain inputs that have been produced from the sheet music. The output layer is going to predict our final velocity. And everything in the middle we'll talk about. So the input layer, we have to decide which inputs to use. That was the first step we tackled. We used some fancy math called a correlation matrix to see which aspects of the notes on the page are most important to guessing its velocity, and we gave the model those inputs. The reservoir is the part of the echo state network that's unique. It's basically just a bunch of randomly connected static nodes that increase the dimensionality of the input data. Basically, it helps find complex patterns that other models might miss. Finally, our output layer is trained to predict the velocity of each given note, meaning how loud a human would actually play that note. For an echo state network, we only train the output layer, not the reservoir, which means it's less work than other models to train. So how do we measure success? We trained both an echo state network and a basic feed-forward neural network on the same data set of 162 classical piano pieces, meaning the models get the sheet music as input and have to predict how a human would play each note. We compared our model to a basic, we compared it to the feed-forward neural network to see if there was any difference, and we measured the loss of each, meaning is what the model predicted close to what the human actually played. And what we found is that our echo state network had a loss of 48.35. You can see an example sequence predicted by the echo state network, where red is the human performance and blue is the predictions. And you can see that it does actually fairly closely follow at least some of the human patterns. In conclusion, this data enough is showing us that echo state networks are definitely a promising new model that could shorten the training time of expressive music generating models and possibly produce better results. But what we are currently missing is a comparison with the feed-forward neural network. So our future work which includes the paper that we're currently working on, will have to have loss value comparisons between different models, and that's kind of our next step to get those numbers so we know how effective the echo state networks are.
Thank you. Good questions. Why reservoir computing? Why not LSTMs or something else?
Yeah, I mean, a lot of the basic types of models have been tried before. I think LSTMs were done. I can't recall the name of the paper, but why we wanted to try reservoir computers was because for specifically time series data that has like a lot of complicated connections where, one input might the way the output for one input might depend on what the input was 10 ago or 15 ago, depending on kind of like a complex pattern in the music, which this, music is a very complicated time series because depending how fast it's playing, 10 time steps might be 10 seconds in the future or 1 second, and it could be anything. So finding those complicated patterns in time series data and turning it into like extrapolating those features or whatever is something that I think reservoirs have often been used for, since the point of a reservoir is to take a less dimensional input data and turn it into more dimensions.
Okay. Excellent. Thank you. More questions for Theo? All right. Thank you again. We blew through the break, but that's okay. If you need to take a bio break, feel free to do that. Otherwise, we're going to continue straight into session 2 with Abigail. And hopefully we'll have a bigger break, or actually a break after this session with 4 presentations. It is loading something.
Oh. Okay, does that look all right?
Yep. Now we can see your slides. Yeah. Okay. Good. Perfect.
Hi, I'm Abby Chable. I'll be exploring the potential of Idaho fescue as a key vegetation for green roofs in Portland, Oregon. Imagine urban rooftops transformed into thriving green spaces, cooling our cities, managing stormwater, and providing essential habitats for wildlife. Green roofs are a revolution in urban sustainability, helping cities become greener and more resilient. But this transformation isn't as simple as planting a few flowers. The key challenge lies in selecting vegetation that can thrive in the specific climate of each city. In Portland, Oregon, we face the dual extremes of increasingly dry, hot summers and cool, wet winters, making the choice of vegetation even more crucial. To understand which plants might thrive on Portland's green roofs, we must consider their photosynthetic pathways. C3 is common, but less efficient in hot, dry conditions. It is also known for its high water loss. C4 is more efficient in warm, sunny environments and is known for minimizing water loss. CAM plants uptake carbon dioxide at night, reducing water loss but limiting daytime activity. My research compares these pathways to determine which is most suitable for Portland. Among these pathways, Idaho fescue stands out. It's a C3 plant known for its cold tolerance and moderate drought resistance. These traits make it a strong candidate for green roofs in Portland, offering potential over other commonly used species. My research evaluates Idaho fescue using the Photo3 model. This model simulates C3, C4, and CAM photosynthesis using mechanisms to account for each pathway's unique traits. It calculates key plant functions based on environmental inputs like soil moisture and temperature, as well as plant parameters like leaf area index and points of stomatal closure. To model Idaho fescue's performance, key physiological parameters were integrated into the Photo3 model using data from various studies like the ones mentioned in the slide. This helped simulate Idaho fescue's performance under Portland's Mediterranean climate. After refining data from each study, I identified an estimated leaf area index alongside onset and complete stomatal closure points for Idaho fescue, both crucial for understanding its water use efficiency and carbon assimilation rates. Here, using a piecewise linear function, I highlight the onset point of stomatal closure and the complete point of stomatal closure using study-collected data. I ran simulations for Idaho fescue, as well as previously parameterized plants, Botella gracilis, a C4 plant, and Sedum album, a CAM plant. Each plant's performance was assessed under identical weather conditions to ensure a fair comparison. Idaho fescue exhibited the highest daytime transpiration rate among the 3 plants. This is crucial for cooling and stormwater management, a strong indicator of its potential for green roofs in Portland. Carbon assimilation rates revealed that Idaho fescue performs steadily during daylight hours, typical of C3 plants. However, Botella gracilis, our C4 plant, showed a higher peak, reflecting its efficiency in warmer conditions. Idaho fescue's stomatal conductance increased rapidly at sunrise, maintaining a high level throughout the day, which is essential for effective photosynthesis and water use. Botella gracilis, while efficient in warmer climates, struggles in Portland's cold winters. Sedum album, a popular pick, known for its superior drought tolerance and low maintenance, may not provide quite as much stormwater retention as Idaho fescue. Future studies should focus on field trials of Idaho fescue on green roofs, particularly monitoring its performance across the seasons. This will provide real-world data to validate its suitability. Further research into soil substrates, watering regimes, and other management practices will help optimize green roofs, ensuring that plants like Idaho fescue perform at their best. In summary, Idaho fescue stands out as a strong contender for green roofs in Portland. Its higher transpiration rates and resilience to cold make it well-suited for enhancing urban sustainability. By choosing the right vegetation, we can make our cities greener, more suitable, more sustainable, and better equipped to handle the challenges of urbanization. Future research and practical trials will further refine our understanding, ensuring that green roofs become an integral part of sustainability strategies, not just in Portland, but in cities worldwide. And that concludes my presentation. Thank you so much for listening.
Thank you. All right, questions from the audience? In your carbon assimilation plot, and also I think there was another one, you had, the curve looked really nice, but there were a couple of like dips that looked like odd or like outliers. Do you know what that was? Was that like cloud coverage or something?
Yeah, it likely was something along those lines.
Okay.
Yeah.
Okay, so some noise basically.
Yes.
Good. Good. What else? So yeah, any other questions? How much was done experimentally? You mentioned you validated some things, but how much was simulation? How much was experiments of your project?
Sorry, I don't understand the question.
Did you do any experiments or did you only do modeling?
Oh, I mostly did modeling.
Okay. And did you validate your models with actual data?
Yeah, the models were created with extracted data from studies on Idaho fescue.
I
So,
see.
yeah.
Okay, great. Good, thank you. All right, if there's no other questions, we'll move on to Artem.
One sec.
Thank you, Abby.
Should I share my whole screen or just the tab?
It's just the presentation. Yeah,
right.
That looks good. Okay.
Yep.
Whenever you're ready.
Hello, I'm Artem Arifev, speaking with you today from Oregon in the US. My project explores the possibility of integrating chaos with electronic controller circuits for emergent useful behavior. A controller circuit is an electronic circuit designed to manage the operation of some other system. It takes input in the form of signals, processes the input based on its internal physics, and uses its output to control the other system, as you can see in the diagram below. For example, the controller circuit may play a simulator of an ant that needs to eat as much food as possible. The circuit might receive a voltage signal telling it what's in front of the ant. The circuit would process the signal using its internal components and output a current signal to control the ant. But except that these ants or any other control system might struggle with quickly finding that first bit of food or might get stuck in a recurrent loop. This is where chaos might come in handy, as even real-life ants at times behave chaotically. Chaos is all about unpredictability. Imagine dropping a bouncy ball on an uneven surface and watching it bounce around. Its motion might seem random, except that it's not. We know that the ball follows simple laws of physics. With enough accuracy, you could predict exactly where it would land. But even a tiny error in our assumptions of where the first bounce lands will change where we predict the second bounce to land and so on, causing a domino effect of cascading errors in our predictions. So even two infinitesimally small an example of this is a chaotic circuit. These can be quite simple. Their behavior does not repeat, can only be approximated, and follows an underlying deterministic pattern. The pattern is called a chaotic attractor. Each system has a unique chaotic attractor that represents how it tends to behave. My work explores the possibility of combining controller circuits and chaotic circuits. For that, you would take a chaotic circuit and build a normal circuit around it so that it can interact with each other, which allows the controller circuit to take advantage of the chaos. But building such a system myself would be futile. For these applications, digital evolution is employed. With the technique called genetic programming, you can automatically generate instructions on how to build these circuits while also improving them in real time, the same way natural selection would. And if you have a population of unique syntax trees, you can allow the population to evolve by having trees mutually exchange instructions. Then soon the whole population becomes more successful through evolution. Right. As you can see, mutation might happen or crossover where two trees might replicate and create children, just like in normal biological systems. I implemented a stripped down version of such a system in Python, where evolutionary processes are implemented using a customized DEAP framework. Each individual circuit is built from syntax tree instructions, and they are all simulated with the SPICE simulator. I used it to evolve a single capacitor in a voltage doubling circuit template. Essentially, it was playing fill in the blank. Here, a voltage output that is closer to the voltage input multiplied by 2 is considered more successful. By running it for 40 generations, the average circuit comes really close to doubling the voltage. It comes at 8.9 volts. But even after 3 generations, the best circuit is really close to doubling the voltage. The accuracy of you can extrapolate this approach to build whole circuits, which is quite straightforward by generating several syntax trees. I also simulated a piecewise capacitor circuit, and it displays a chaotic pattern called bifurcation doubling. I also simulated the single transistor chaotic circuit. It proved to be much easier to simulate and required no additional post-simulation calculations. Many of its behaviors are chaotic, and as you can see on the right is its chaotic attractor. I also calculated the power spectrum using Fourier transform of the single transistor circuit, which appears to be extremely fuzzy and mostly free from local maxima, which is a strong sign of chaos. But it also has a very low frequency. In conclusion, my work suggests that integrating controller circuits with chaotic circuits is technically possible. Genetic programming is able to generate unconventional circuits that can take advantage of chaos. For my future work, I plan to extend the genetic programming approach to generate whole circuits, as I've described, by generating multiple trees. And I'd like to generate normal controller circuits that play the ant simulator successfully, even without chaos. Thank you.
Thank you. what will be an advantage of using chaotic circuits versus non-chaotic traditional circuits?
Right. So the goal of the project is to integrate chaotic circuits with, again, normal circuits that behave deterministically. The idea is that chaotic circuits would essentially inject information, free, unpredictable information into the larger controller circuit. And the idea is to evolve the controller circuit so that it can take advantage of such information. For example, you could have an ant randomly, chaotically move around the map in search of food if it doesn't spawn right next to a piece of food. Does that make sense? Does that answer your question?
Yeah.
Do you have any other questions, anyone?
Any other questions for Artem? Okay, thank you again. If not, we'll move on to Parth and Varun.
Yeah, we're both here.
Okay, good. Who's going to share the screen?
It's going to be me.
Okay.
Oh, can you guys see the screen?
Yeah.
Okay.
Can you go in your slideshow? Good, it's looking good, yeah.
Okay. All right. Hello, everybody. Imagine that you were in a hurricane and you lost your most valuable assets, such as your house or a family heirloom. Who do you turn to for disaster assistance? Luckily, the Federal Emergency Management Association, aka FEMA, is there for you. However, there are some issues. Firstly, people may be unaware of the extent to which FEMA can help them. Also, the terminology within FEMA's forms contain intricate niche acronyms. And lastly, there's an excess of forms. So, what is our solution to these issues? Well, we've developed a chatbot in the form of a pre-trained LLM contextualized with form data to answer FEMA-related questions. Our chatbot has advantages over tools like Google and ChatGPT, which we will address later.
So we need to use a process like RAG to enhance the output of our LLM by incorporating relevant data from our vector database. It involves using pertinent documents to augment our LLM's response, ensuring accuracy and making it contextually specific. In order to understand our vector database, we need to grasp vector embeddings. Embeddings basically translate unstructured data into multidimensional vectors with similar vectors embodying similar contexts. You can notice that cat and kitten have similar vector values. Bringing all embeddings together, we create a vector database. You can think of it as a space that stores the words retrieved from our data sources as vectors, and it handles data such as text by creating vector embeddings.
So for our pre-trained large language model, we selected Ollama as a platform to use Mistral AI's open source LLM. Then we used LangChain as the primary Python library in our code because the library is made for developing RAG systems like our chatbot. So for example, take a look at some of the LangChain imports we've used. Document Loader converts the content read from the FEMA forms into a structured format. Community embeddings create the vector embeddings, and Text Splitter splits the form data into smaller chunks for the LLM to process. Other LangChain imports include vector stores, which helps store the embeddings in the vector database. Chat prompt template provides flexible prompts to guide the chatbot's response, and schema document defines the structures and type of data our LLM will expect to read.
PyPDF is an open source library in Python that allows us to retrieve, scan, and break down the PDFs into multiple chunks for the vector database. Separating PDFs into multiple chunks allows the LLM to retrieve only the most relevant chunk of document for the user query. In these images, you can see we've uploaded over 200 documents into our database. Some of these documents include the fact sheets that are 20 to 30 pages long. By having multiple chunks, it results in fewer input tokens and more targeted content for the LLM to work with. Now, for our UI, we decided to stem away from the usual practice of using Flask and opted for Streamlit. It's an open source Python library that allows us to build a web application that's easy to use and coded very efficiently with a minimalistic display.
Now, let's demonstrate the capability of our chatbot with a use case. First, we asked Google the question, what forms do I need to fill out after losing my job due to a hurricane? Well, the information displayed is not personalized. Google provides a list of unsorted links, and we get irrelevant results like what is the EDD relief fund at the bottom of the page. Asking the same question to ChatGPT, we get a better response than Google. However, it's still very vague, using sentences like apply for aid through FEMA or check your state's labor department for specific forms. No specific forms are mentioned though. Finally, we asked the same question to CrisisCom. A concise answer is provided with mention to a specific form called FF104 FY 22228. When we looked this form up on Google to verify CrisisCom's accuracy, we found there was indeed a form for financial assistance.
Our second use case is a person whose small business was ruined by a flood and he or she seeks for FEMA's assistance. As you can see, Google's response to this question was basically a direct copy of the text from FEMA, which doesn't help considering how subjective the situation is. Now at ChatGPT, the response was a little better, and it lists out some meaningful steps that can help the user get somewhat started in the process of acquiring aid. Nonetheless, it still isn't specific enough to the point which our LLM achieves. Lastly, for our model, it's a perfect example of the high-level response that it delivers by considering the user's specific situation and walking them through the process. The model explains to the user how to get started and describes how the whole process would look from start to finish, while adding a backup idea.
In the event our chatbot is asked the question it can't answer, it won't generate an incorrect response. Instead, as shown in the example when asked how FEMA helps with skiing, the chatbot says that it does not know the answer because the data it was trained on does not mention skiing.
At last, some of our future plans for the model include deploying it online to make it accessible to users worldwide. We also want to periodically add newer data as FEMA releases them and continually gather customer reviews from the engagement online to fine-tune the LLM and best cater their needs. Thank you everyone for your opportunity to listen and have a good day. We're ready for questions.
Thank you. Questions? So you mentioned you want to deploy it online. I think that's great. Did you talk to FEMA at all to see whether you could, get some forms earlier so you could train them and, train your model maybe with unique data that they could provide you? Or?
We haven't considered that, but that's a good idea that we could work on post like deployment also.
Right. I could imagine they would be really interested to, see a tool like that can answer cool questions and provide accurate answers, obviously, and they could be supportive of with providing data and whatnot. Yeah. Okay, very cool. Great.
All right, thank you.
Any other questions? Okay. Thank you again. Is Daniel online? I don't see Daniel. Okay, no Daniel. He was the last speaker of the session, so that means we have an even bigger break, and we will continue our third session at noon Pacific time. I will put up a little slide here. Let me show you. And as I said, I will keep the Zoom session active so you folks can disconnect if you'd like, but you don't have to. You can just stay online. And we'll continue at noon Pacific time. Until then, yeah, take a break. All right, folks, welcome back. We're gonna start session number 3, and Alicia Hopper is gonna be the first speaker.
Excellent. I will just share my screen then.
Yep, you should be able to.
Excellent. Okay, and then we'll put this here.
Good. Okay. looking good. Yeah.
Everything. And oh, I forgot to click the button. No, please.
All right. Good to
Okay,
go.
there we go. All right, so I'm Allie Hopper, and I'm presenting on capturing active transportation counts at intersections using Ultralytics YOLO V8 image and video tagging. So this is the project I did this summer, along with Dr. Tammy Lee and Dr. Sarisha Kothuri. So just as an introduction, we're looking at active transportation counts. So that's like counting bicyclists and pedestrians. And so right now, those counts are done by manual counts, automated counter devices, and some machine learning. So then when we talk about manual counts, they're the most common method, but they do take a lot of time. You're going to kind of have someone out on the street who's looking for things. You're going to have a video camera that's recording, and you're going to be reviewing that video data. So that can just be a really resource intensive process. So that's kind of what this looks like here. You've got someone who's kind of out there taking down notes. You've got a spreadsheet. It can take up to like 3 times the length of video that you take. So that can be really hard, even though it's very accurate. And so then for automated counting devices, there are a lot of them on the market, but recently they've been very focused on like cars. There is some more look into pedestrians and bicyclists as of recent, but they can still be not exactly exact or expensive. And so more work is needed there. And so then for machine learning and computer vision, it's kind of a promising alternative there. There's a lot of options available for models. The research mostly focuses on self-driving vehicles and kind of detecting pedestrians for that, but that also works here. So you're going to need a model. So the model is going to look kind of like this. You're going to have an image that you're going to take as input, and then you will kind of annotate this. So this is actually from the model that I built, annotating this. And then on the right is kind of what the model looks like under the hood. So to choose a model, we chose the YOLO model, which stands for You Only Look Once. And so these models are in a lot of the research. The latest version is version 8. We use the small size, which is not actually that small if you look at the parameters in there. So to train the model, we used Python. You could also use the command line. Python is easier, I've found. And then you're going to need training data with images and annotations, and then also a GPU computer to make things go faster as well. So for the training data, we use the EuroCity persons data set. So that's about 40,000 total daytime images, which is a lot of images. And so then those images are annotated by pedestrians, riders and bicyclists, scooters, etc. So we had to convert some of this data. So originally the bounding box was kind of annotated using the corners of the box, but we needed to convert it into the middle of the box and then kind of that difference to the edges of the box. So we had to run some programs there. And then the images that we used to train were all taken in the daytime because we were looking at intersections in the daytime. They're not from far away, and we're not looking at occluded pedestrians. And we had to divide the data into 6 batches just for data limits on computers so that it can all get kind of trained. So here's some of the training metrics. So you can see on the left, this is during the first batch of training, that the precision and recall are going up. So that's like false positive, false negatives. And then on the right, you can see the precision recall curve. And so there you can see that kind of as the confidence increases, you get what you'd expect, where the precision goes down and the recall, or the precision goes up and the recall goes down, which is kind of a balance there. And so to use the model, you're gonna want input video. You have to select the regions to count in. I've written a Python program, and then it should output kind of this video that has annotations of the pedestrians. Unfortunately, we ran into some issue with the graphics programs. So as you can see here, it's looking a little wonky right now. It looks like the model is doing okay, but selecting the region isn't quite working. So there's a little bit needed to be done there just to kind of fix that. So for conclusion and results, we have a rate for pedestrians of 0.551. That's kind of like accuracy. And then rider and bicyclist is 0.455. And using video data, we are expecting a higher level of accuracy there. So then for further work, we're looking on maybe training on more difficult data, more testing and validation, other models, fixing up that Python graphics thing, and then looking at maybe using it outside of intersections, looking at bikes and bike lanes or other things. So before I finish up, I just wanted to give a little talk about the lessons that I've learned throughout this project. I've learned a lot about how many research papers and data sets exist, and then also just kind of about how the path to the end is, as everyone always says, not linear. So thank you for listening. And then if there's any questions.
Questions for Ali, thank you. Definitely not linear yet. None of the research path tends to be linear. Sometimes chaotic, as Artem would say. Good, any questions? So you focused on pedestrians and bicycles too, is that right?
Yes, that's correct.
I was thinking about scooters. That seems to be another modus of transportation that is very popular. What would you need to do if you wanted to do scooters as well, count scooters?
Well, so right now the model is trained also on scooters. It has a little bit less
okay.
data on scooters just because there were less scooters in the EuroCity data set.
Okay.
I think that just with more training and like kind of trying to focus on that, you could get that number up higher and then actually include it in the count for counting them.
Okay. So it wouldn't be a big step at all. Yeah.
They would not be, no.
Yeah. Okay, cool. What would it need to deploy what you've done, like in the real world scenario?
Well, it would definitely need the YOLO model has this kind of built-in like graphics thing where it can count in this video, but as you can see, it's not quite working exactly as you might expect it to. And you can't actually, as of right now, like output the counts to like a CSV file or anything, which is kind of problematic. And so there would need to be some work done on like that side of like you have the model, you know how it's trained, but how do you actually like get those counts into like a more usable format?
Okay, great. Thank you. Good. Any other question for Ali? All right, let's move on to Lyndon then. Thank you, Ali. Lyndon.
Thank you. Give me a moment to share my screen.
Yeah, go ahead.
Okay, so here's my presentation. Modeling the impact of autonomous vehicles on travel and land use with an agent-based approach. I'm going to quickly set up autoplay and we can begin.
Okay, looks good. Thank you.
Okay, so for those whom I haven't met yet, I am Lyndon Fay, and I participated in the NSF REU program these past couple months with my mentor, Dr. Li-Ming Wang, to bring to you all the project that I will be presenting today. Before we get into our project, let's review what agent-based modeling, or ABM, is. ABMs are a powerful tool used to simulate complex systems, which consist of variables called agents that interact with one another in an environment. Compared to other modeling approaches, instead of relying on more explicitly defined formulas or procedures, each agent has a unique set of rules and behaviors, which update as they adapt to their environment. Each agent thinks, learns, and makes decisions for themselves, which allows for many different emergent outcomes. ABMs can also help us better understand the impact of AVs, including travel behaviors and energy consumption, but it also faces many challenges, such as the complexity for each agent to simulate realistic situations. I will address some of these concerns and describe a proof of concept for analyzing certain effects of AVs. In the current version of our model, each agent is first defined into one of two main types, an employer or a worker. These classifications determine their actions and behaviors, as well as how they interact with each other and the environment around them. Upon initialization, the agents are then placed into a grid. Workers are able to share the same space with a maximum capacity determined by a monocentric density gradient, while each employer is given their own respective space on the grid. Next, each worker is randomly assigned to an employer. Employers can have multiple workers at a time, however far they might be placed in the environment. Once assignments have been fulfilled, each agent starts to interact with their surroundings and act out all of their behaviors. For employer agents, their job is to keep track of all of their employees. As for the worker agents, they have a couple more actions and decisions to make. Each day, all workers can choose whether or not they want to ride an AV to work. This decision is made after evaluating the cost per distance, which is set by the user, and the round trip distance between the worker and their employer. Their decision is determined by this probability formula on the right. The other main behavior for each worker agent is to relocate for the next day if they decide it's too expensive to ride an AV to work. This action is determined by a second probability formula, the relocation formula over here. Ultimately, there will be two important variables we'll keep track of for each worker agent, their round trip distance and their VDT. VDT shows if the worker actually decided to take the AV to work or not. It will either be the same as their distance or it will be 0. We will then show our graph for one run of each worker's round trip distance and VDT in a series of graphs. This graph here shows the frequency of round trip distance for all workers in a particular month of the model. This graph shows the normal distribution of all workers' round trip distances in a histogram. Compared to the previous bar graph, this one is more generalized, and you can also see the highest frequency via the probability density function. Compare the graph for distance to this new VDT graph on the right. Notice how some values have moved to the 0 distance range, as a handful of workers decided not to ride the AV to work on this particular day. This plot shows the relationship clearer, where we can see that for many of these distances, there are some amount of workers that choose not to take the AV to work, resulting in them having a VDT of 0, in contrary to some other agents with the same distance. These are heat maps showing the distance summations on each space in the grid environment. Green spaces represent employer spaces and white spaces represent empty spaces. And then the rest of the color squares follow the color legend on the right, depending on the sum of round-trip distances of all workers residing on that space. The heat map on the right represents the day after the left heat map, where if you look closely, some workers have relocated upon evaluating the previous day's cost per distance. Now compare these two heat maps. The left one is for distance while the right is for VDT. We can see that some spaces on the right have grown darker. This is due to some workers not riding the AV to work, resulting in them having a VDT of 0. Finally, here is a batch run of our model with different initial values for cost per distance. We can see that as cost per distance increases, the average VDT will go down, as workers will be less inclined to ride an AV to work due to the more expensive price. In the future, we plan to expand this model, adding more policies as roles, as well as making it compatible with GIS, and allowing it to use real-time data to influence land use and the behavior of our agents. That is our project. Thank you for listening, and a special thanks to Dr. Teuscher and the REU committee for making all this possible.
Thank you. Questions from the audience?
Would this be possible to work in real time?
Yes, we plan to put this into a GIS model and use Portland as a blueprint to see how they will interact in a real-time environment.
Good luck.
Thank you.
Could you easily transfer your model to a different city?
I think so. Our plan right now is to move it from the standard Mesa grid environment into a GeoMesa environment. That allows for the implementation of other mapping systems.
Okay, cool. I'm sure other cities will be interested in.
Mm-hmm.
Great. Other questions for Lyndon? Good, thank you. We are right on time. Next up, Rowan and Josh.
Hello? Can you hear me, Professor? Okay.
We can hear you, yeah.
All right, let me share my screen. And then, okay.
Ready.
All right. So our project was linear forecasting, predictive stock market trends. My name is Rohan Shah, and I'm a sophomore at UIUC.
And my name is Joshua Konagala, and I'm also a sophomore at UIUC.
So our goal for this project was to create a machine learning model that could accurately predict future trends of stock data with previous historical data and sentiment data, which is from news sources. And we plan to do this through APIs, regression models, and Python models as well. So why did we choose this project? So previous stock models rely on historical data, which is usually just not enough. And through using sentiment data, we convert article text into scores and add it to the machine learning model. So some related works that people did were stock prediction using regression analysis, which is like linear regression. And another one was through support vector machines, which were like organizing different data points into different classes. Then there was also stock prediction using principal components and also stock prediction using sentiment analysis, which I'll be explaining later into how we're incorporating that into our project.
Okay, so the APIs we used for the stock price data collection were Yahoo Finance, the Google Sheets API, and we used Python to calculate these values. And we pulled data from the past 10 years from 8 companies. Here are an example of some of the data we pulled. For example, open, high, low, close stocks. We used all of these data to essentially help predict these values when we put it in to our Python script.
And so to gather sentiment data, we use Vader sentiment analysis, which calculates the scores, which I'll be explaining on the next slide. Beautiful Soup, which grabs the news articles, and FinViz was the source of the news articles, essentially. And so here you can see all the sentiment scores of all the 8 companies we chose, where it's from -1 to 1. Being closer to 1 means a higher public opinion. Closer to -1 means a lower public opinion. And this was just from the past week.
Okay, so the regression tactic we used was MAE, mean average error, and this basically calculates residuals again from the past 10 years of data we pulled. Using these past residuals, it can accurately predict trends. For training and testing, we split the data about 80% for training, 20% for testing, and we used Skit to do this on making predictions on the testing data. The MA implementation on the stock model, we again used Skit, and we used features of SMA20, EMA20, volatility, ATR, and other data measures that we inputted into MAE for the residual calculations.
And so to incorporate sentiment analysis in the model, we merged it with stock price data that had the same dates on the spreadsheet. And through this, the model was able to learn how sentiment scores correlated with price movements in the market. And so here you can see our results. We separated it into training and testing data sets. And for the model without sentiment, we can see how the training data set had a higher MAE compared to the testing data set. And with sentiment, we can see how this value decreased for the training data set, whereas the MAE for the testing data set really didn't change that much. And so comparing these side by side, we can see how companies like Microsoft and Meta for the training data set had a much significant decrease in their MAE because of their high value stocks. And this was not the case for the testing MAE, where you can see for Microsoft, when we used sentiment, the MAE actually went up. So it didn't have much of an effect on the testing data set itself.
Basically concluding this, we adding sentiment analysis actually increased predictions by an average of 3.2%. The predictions became better for stocks in the training set, but not really for testing, and results are fully conclusive. Applications we can use it on qualitative analysis, risk management, and investment and trading strategies. However, it would need to be a little more accurate with the variability of a lot of data.
And so some concerns and next steps. So a big concern was a limitation on access to news articles. These news articles also covered mainly major companies, not smaller ones. And we also want to expand the model to companies in other industries besides tech itself. So any questions?
Thank you. Questions? I was wondering, and maybe I missed that, is your work unique in the sense that you're the only ones applying sentiment analysis, or did anybody else do it?
No, there have been past projects
Yeah.
that have done that. That was
Okay.
just our approach. We chose that after like looking at all the past works, we felt that that was like the best approach. It's kind of what we wanted to do in the beginning.
Yeah.
So
Okay.
yeah.
That's great. But did you also compare with that existing work then?
Yeah, we were able to do that. Yeah, that's why we said there was like a 3.2% increase in accuracy. However, the problem was the sentiment analysis data can sometimes be wrong in the case that, like,
Yeah.
for example, articles could be biased towards one or another predicting trends. So overall, the trend actually maybe have decreased a little bit, like predicting it, but yeah.
Okay, no, I thought your 3.2% was without sentiment analysis, but using your approach.
No,
So that is
yeah.
compared to related. I see. Okay.
Yeah.
Okay, so that's pretty cool. Yeah, good. I mean, this is a problem that has been, well, people have trying to solve that for for decades, basically, right? So
Yeah, no, the main problem was just getting access to news articles. It was so hard because APIs limit the amount of requests, and there's always like a bunch of problems with that. But yeah, we tried our best.
Yeah, good. No, great work. Yeah. Okay, any other questions? All right. Yeah, great. Thanks again. I think these were excellent results. Yeah. All right, we have Bethany coming up next on my list.
Can you hear me?
Yeah, we can hear you.
Okay, great. I'm going to share my screen now.
Yeah, go ahead.
Okay, let me know if you guys can see this.
We can see your slides. Yep.
Okay.
Looks good. Okay, go ahead.
So, hello everyone, I'm Bethany Navarro. Today I'll be discussing how reinforcement learning is advancing the field of assistive robots. RL trains agents to make decisions by rewarding positive actions and penalizing negative ones. This approach is instrumental to developing smarter and more adaptive assistive robots. Assistive robots are designed to help people with physical or cognitive impairments. They play a pivotal role in various areas. One area would be elderly care, where these robots assist with daily activities, medication reminders, and social interaction. Another would be rehabilitation, where they support physical therapy by aiding patients with motor impairments. These robots enhance the quality of life by providing both practical help and emotional support. So our project focuses on several key objectives, which would be developing RL models to boost the capabilities of assistive robots, testing these models in simulated environments to refine their performance, and evaluating their effectiveness and adjusting for real-world applications. The goal is to create robots that are not only more efficient, but also more adaptable for the needs of users. Let's dive into the carpool environment. A classic RL benchmark here, an agent task is to keep a pole balanced on a moving cart. The agent receives feedback based on its actions. So this includes the cart's position, velocity, and the pole's angle and angular velocity. The agent can move the cart left or right to maintain balance. So the setup helps us understand fundamental RL principles and test algorithm performance. For the cart pull task, we applied several RL algorithms, including DQN and Q learning. So the training involves running multiple episodes where the agent learns to balance the pull by receiving rewards for successful balance. Key metrics like training duration and average reward help us gauge the model's effectiveness. Moving on to the fetch pick and place environment, where the robot manipulates a block to a target location. This task requires precise control and manipulation, providing a more complex challenge compared to cart pull. In this environment, we used proximal policy optimization, otherwise known as PPO, and soft actor critique, which is SAC, algorithms. These models help the robot learn how to accurately move the block. We evaluate the performance based on success rate, average reward, among other metrics. Feature selection is crucial in RL as it reduces the dimensionality of the problem and enhances model performance. By focusing on the most relevant features, we improve learning efficiency and decrease computational costs. In our project, we applied feature selection to the fetch dataset, identifying the most relevant features that impact task performance. Techniques like correlation analysis and random forest importance were used to refine the dataset, making the learning process more efficient. Here, we visualize the training results for the cart pull environment. This illustrates how the agent's performance evolved over time. Similarly, for the fetch pick and place environment, we have visualizations of training results. Balancing exploration and exploitation is key in RL. So strategies like epsilon greedy and softmax exploration impact training efficiency and model performance. Fine-tuning these strategies can significantly enhance the accuracy and effectiveness of the RL algorithms. So we compared various RL algorithms, including Q learning, DQN, PPO, and SAC. The comparison highlights differences in training time, reward efficiency, and overall success rates, guiding us towards the most effective approaches. So throughout the project, we encountered challenges in high dimensionality and sparse rewards. Solutions included feature selection and rewarding shape. We also addressed training stability through hyperparameter tuning. So looking ahead, there are exciting opportunities for further research, which would be integrating with real-world robots, development of advanced algorithms, and expansion of feature set and environments. So these areas promise to push the boundaries of assistive robots. In summary, RL significantly enhances assistive robots by improving adaptability and efficiency. Some key factors include effective feature selection and fine-tuning of algorithms, which contribute to better performance in simulated environments. RL demonstrates great potential in making assistive robots smarter and more capable. The insights gained from this project underscore the importance of RL in advancing robot decision-making and task execution. So I just wanted to have a big thank you to my mentors, Manashef and Cheyenne, for their help and guidance with me through this project. And then also a thank you to the NSF for funding this REU. Thank you for your attention. And does anyone have any questions?
Thank you. Time for questions. did you you mentioned DQL, I forgot the abbreviation, but I was going to ask, did you also try deep reinforcement learning?
I tried just a little bit of that, but I don't know, I had a bit of I guess a bit of a time crunch when it came to that.
Okay.
When we started getting more deeper into those ones, the time was already running up.
Yeah. Okay, good. Yeah, that seems to be like state of the art. A lot of people use that, I guess, but it's also compute intense, obviously, and yeah. Okay, good. What about the scalability of your approach? Reinforcement learning sometimes, or I should say maybe more often than not, has scalability issues. But did you look into that? How your approach would scale to larger problems?
Yeah, so we had a pretty like large number of what is it called? We practiced I began like on a data set, and
Okay.
we definitely scaled up from that. It was
Okay.
Yeah, it was pretty big in my opinion. I think it was pretty big.
Okay, good. Great. And you get extra points for doing LaTeX slides.
Thank you.
Nobody else has done that so far. Good. All right. Any other question? Good. Thank you again, Bethany. All right. We have, last but not least in this session, KB.
All right, I'll share my screen.
Yep, go ahead.
Do you see my screen?
Yep, looks good.
Got it.
Go ahead again.
Okay, hello, my name is KB. I study computer engineering at the University of Illinois Urbana-Champaign, and my project name is Forecasting Quarterly US GDP using LSTM neural networks. GDP, or gross domestic product, basically measures the strength of an economy of a country in a period of time. GDP forecasting is a extensively studied subject for many economists and policymakers. I first started my project by gathering economic data from the Federal Reserve website, and after doing data processing and cleaning, I performed wavelet decomposition and made two models for both the high frequency and low frequency components, which is a method used in another paper. The reason why I used LSTMs was because it's a type of RNN that basically has the ability to forget some information from the past, which is why it is often used in time series forecasting. And I use certain number of economic indicators as inputs, first being past GDP, because it is a time series forecasting, and I use CPI index, which basically measures inflation, PCE index, which measures how much people are spending money. And then I used industrial production, exports, federal interest rates, and unemployment rates. These are the indicators that I thought would most affect GDP. For data processing, I gathered quarterly GDP economic data from 1960s to 2020, which in total made up of 240 rows. After doing data cleaning, I used waveform analysis, which is a method to break down inputs into different components, in this case being high and low frequency components. Wavelet analysis can accurately point out peak delay relative to a input and output, which is perfect in this case because GDP is known as a lagging indicator. The low frequency components measures the overall trend of the inputs, and the high frequency components measures the short-term fluctuations. And then I use min-max scaling to scale the data from 0 to 1. By putting inputs into a similar range, you can have faster convergence, more stable and faster training in general. I then split the data into 70% of training, next 15 validation, and the remaining being testing. I used this method because to keep its temporal state of data. And then I used rolling window method with 4 units of input and the 5th one being the output. I then fed those 4 inputs of low frequency and high frequency into a separate LSTM and combined it with a singular loss function. Every unit has a rectified linear unit activation function. I used this because of its simplicity and its standard use. It basically clips the negative values to 0. And it's overall easier to and faster to train. To compile, I utilized early stopping to prevent overfitting the model. I then used learning rate scheduler. For optimizer, I used ADM. And then to compile, I used a mean square error loss function. MSE basically squares each predicted values and finds the average of them. I used it because of its, again, simplicity and its standard use. This is the predicted GDP on the testing data. As you can see, it had a 6.28% error. The biggest amount of error coming from 30 quarters after 2011, which is 2020, being COVID, so it's basically an outlier case. This model, compared to other prediction models such as linear regression or LSTM models without the wavelet analysis, can be seen here. The linear regression had a 15.76% error. A traditional financial seasonal ARIMA model had a 15% error too. Regular LSTM had an 8% error, and the wavelet analysis combined with LSTM had a lowest of 6.28% error. To improve and next steps, you can fine-tune more parameters, experiment with different inputs and economic indicators, and you can increase the number of predicted quarterly GDP. Right now, it is only predicting 1 quarter in the future, and you can expand this method to predict other indicators such as federal interest rates, stock markets, housing markets, and more. And that is it. Thank you for your attention. Let me know if you have any questions.
Awesome, thank you. Questions from the audience? What other indicators could you add to improve your performance? Maybe things that others haven't done.
Right, you can include the treasury yield rates, for example, like 10-year yields, which is pretty important for GDP too.
Okay. And how much do you think you could improve your performance?
I think maybe 1 to 2%.
Okay.
Because it is really difficult to get it under 5%. Yeah.
Yeah, that was my other question. What state of the art, what other related work has achieved? So is 5% sort of like that's the area you're talking about?
Yeah, the state of the art has, from what I've seen, has lowest being 5.5 to 10% per.
Okay.
range.
So 6 is actually pretty good.
Yeah, 6 is pretty good with this method.
Yeah, all right. Very cool. Good. Other questions from the audience? Okay, if not, we are at the end of session 3. And we're going to have a pretty good break till 2 o'clock Pacific time. So an hour and a half, a little less than that. And then we'll do the last session, session 4. Again, we spread out these sessions a bit to accommodate the different time zones that folks are in. So we'll meet again in a little bit less than an hour and a half, 2 o'clock Pacific time, and I'll keep the Zoom going. You can just stay online if you'd like. So see you soon. Let's get started again for the last session. If all goes well, we should have 10 presentations, and we're going to start off with Adrian.
Yeah, okay, can you hear me?
Yep.
All right, let me share my screen.
All right.
Okay, can you see this?
Yeah, it's coming up. Yep.
All right.
Good. That's good. Yeah. Whenever
Okay.
you're ready.
My name is Adrian. I'm a high school intern working under Dr. Teuscher in Teuscher Lab. And my project is a microcontroller-based MEM capacitor emulating platform. That's a mouthful. That's a mouthful. Okay, so what is a MEM capacitor? First, we need to understand what even a capacitor is. So it's a passive circuit element that stores electric energy. It relates charge and voltage, and it behaves linearly. Meanwhile, a MEM capacitor stores electric energy as well, but it relates charge and magnetic flux, but it behaves non-linearly. And you'll see that in the pinch hysteresis loop soon. They don't even exist either. Only things mimicking their behavior do exist, such as emulators. Now, why is a MEM capacitor even important? Well, I mean, once they're even created, they have a lot of potential uses in the future in neuromorphic computing, as well as resistive random access memory and just non-volatile memory as a whole. So what did I do with MEM capacitors? Well, I simulated their behavior. I simulated a MEM capacitor emulator on LT-Spice. I breadboarded a prototype, as well as created an online platform that will allow people to test on that circuit. Now, why this project? I chose it because I want to be an electrical engineer, and it's pretty hardware as well as software intensive. And once Dr. Teuscher told me about it, I was pretty interested. So simulating their behavior, I simulated a MEM capacitor emulator that I found in a paper on LT-Spice just to see its behavior prior to actually like breadboarding it. And here on the right, you see the proposed MEM capacitor emulator circuit. And on the left, you see what I actually made in LT-Spice. The only change I really made was a change in the analog voltage multiplier. And actually, this is the first time Dr. Teuscher will see this as well. I was able to get a pinched hysteresis loop yesterday when I ran the simulation. Now, this is like a telltale sign of MEM capacitor behavior. I think the one on the top looks more visually pleasing, but yeah. Okay, so now I'll talk about the breadboarding as well as the prototyping of the circuit itself. So I've had issues with getting the analog voltage multiplier part of the circuit working, but here's the circuit itself. It looks pretty jumbled and messy. So most of this is actually just the analog voltage multiplier with like the resistors setting the denominator. And here's like actually a diagram of what everything is. Now you see, yeah, pretty much like all of this is just the analog voltage multiplier. Meanwhile, the diodes, the capacitors, the op amps, that's just this. And it's disconnected because I was just testing the analog voltage multiplier. And that brings me to the online platform where the voltage the circuit will be characterized. So current as well as voltage will be measured. They'll be plotted on the online platform. And the voltage will be measured by a Raspberry Pi oscilloscope shield. So on the right is the software for it. It measures the voltage, and my hope is to modify the source code. Well, I already modified it, the Pascal source code to output the voltage to a CSV file, and then the CSV file will be the data from the CSV file will be plotted onto the website so that people can see the Raspberry Pi web server that has been set up so that people can see the results after sending an input signal where they customize the amplitude of the signal and the frequency so that they're able to test on the server remotely. Not on the server remotely, on the circuit remotely. Now, my next steps would be to implement a current measuring method so that it can be integrated and you get the charge so that you could then plot voltage and charge and see the pinched hysteresis loop. as well as create a crossbar configuration or just an array of mem capacitor emulators. That would take a lot of time, and I really want to do that. And as well as just complete the web server so that it allows for the user to modify like input signal and all of that. Now, I took a lot away from this this internship and just this experience as a whole. I learned many things about electrical engineering, and I mean, for that, I have to thank Dr. Tusher for this opportunity. Like really big thanks to Dr. Tusher, as well as all the interns in tlab for providing me assistance whenever I needed it, such as like Daniel, Hussein, Artem, and everyone in this Zoom meeting for listening. And now I'll open up the table for questions if there are any questions. Thank you.
Thank you. Awesome. Thank you. Yeah, questions?
Was awesome. I was wondering, so the Prince hysteresis loop, is that response to a sinusoidal input?
Yeah, it's the input was I believe 2 hertz frequency, and it was like 1 amplitude. Yeah, 1 volt amplitude, but yeah, it was sinusoidal.
Awesome. That was done with Spice, like
LT Spice, yeah. I don't know
oh,
LT Spice.
right. That's really cool.
Yeah.
How would you go about the crossbar simulation / implementation?
I still have to think about that. It
Okay.
would, yeah. I mean, it would also require like I change a lot of things about just like the system for measuring the voltage, because I think yeah, the oscilloscope can only measure one signal. So I would, to measure the different intersections, I need like some other method that would allow me to measure several different signals, maybe with like just using like the GPIO pins on the Raspberry Pi and like a analog to digital converter or something to be able to measure the voltage, and then send that to the website and plot it.
Yeah. Very cool. Good. Yeah, it's great that you got the pinched hysteresis.
Yeah.
It's awesome.
Yeah.
All right. Thank you. Let's move on time to EJ and Chloe.
Hello, can you hear me and see me?
Yeah.
All right, let me share my screen. Let me just, is my screen showing?
Yep.
Okay. And go.
Good afternoon. Our project consisted of testing soil moisture, plant health, and water management, and for the implementation of green roofs within the CNMI. My name is Chloe Singh.
And I'm EJ Giri, and we're from the Northern West College. Imagine buildings that are not just structures, but living, breathing ecosystems. Green roofs could transform our landscape, offering cultural connections to culture and creating tourist attractions while addressing environmental challenges.
Saipan faces severe environmental challenges like soil degradation, poor stormwater management, and the urban island heat. We tackled these issues by investigating the potential of green roofs by monitoring soil health, composition, and stormwater management.
Why does this matter? Healthy soil is the backbone of our ecosystem, supporting plant growth, regulating water, and even helping combat climate change by improving soil health and managing stormwater. We not only protect our environment, but also improve our quality of life. Our solution is simple, yet powerful, integrating green roofs across Saipan. These roofs can enhance stormwater management, create a baseline that optimizes the overall soil quality, determine what vegetation and soil would be more resilient to the environmental condition.
We began by collecting soil samples from different areas, focusing on pH, moisture retention, growth rates, detention, soil composition, and evapotranspiration, also known as ET.
In addition, we constructed green roof models using local soil samples to replicate real-world conditions. These models helped us simulate the effectiveness of green roofs in managing stormwater and supporting plant growth. This is done so by focusing on comparing soil samples from different areas to control store-bought products. The first model is the gravimetric method. We measured how much water the soil lost by weighing it before and after a set time. The second method is Penman-Montev method. This method uses meteorological data to estimate evapotranspiration.
Soil composition is vital for understanding water management and plant health. High sand content in our samples showed dry conditions and low nutrient availability, and indicating that the addition of different materials might be necessary. We measured physical, chemical, and biological properties as a soil quality index to determine which soil would be best suited for green roofs. Our analysis showed variations in pH, moisture retention, growth rates, and runoff coefficients. We also looked at how different soil properties are related through correlation tests. We found that all properties have a statistically significant relationship with a p-value less than 0.05. Sample pH and growth rates indicated low pH level.
For our detention experiment, the correlation between gravimetric ET levels and runoff coefficient is weak, suggesting that runoff and ET are largely independent. This indicates that there are different factors influencing these processes. This graph shows how evapotranspiration varies by soil type, comparing the two methods mentioned earlier. Notice on how the black dashed line is steady while the colorful lines fluctuate. This variability underscores the importance of selecting the right soil. This box plot then compares all soil types which falls below the control, indicating that local soils generally retain less moisture. With significant variability in ET levels, this suggests that local soils may need amendments to match the performance of the control. Our findings suggest that soils from areas like Koblerville, Garapan, and San Roque show potential for green roofs, as they exhibit similar qualities under the control pot mix in some respects. However, they still fall short in key aspects like evapotranspiration levels.
The short duration of our experiment, limited to just 12 days, constrained our ability to observe long-term trends in ET and plant growth. This time frame did not account for the seasonal variations that are critical in Saipan's climate. Another limitation was the limited number of soil samples from these locations. The sample size may not represent the full range of soil conditions across Saipan, which could affect the generalizability of our results.
Future research should involve long-term experiments that cover both the wet and dry season in Saipan. This would provide a more comprehensive understanding of how ET levels and plant health vary over time, giving more reliable data for our green roof applications.
Additionally, exploring a variety of vegetation and incorporating advanced technologies such as remote sensing and GIS could create a more accurate soil quality map.
The work was supported by the altREU program at the Portland State University. We would like to thank Northern Maryland College and the Compass program for their assistance. We're open to questions. Thank you for your attention and interest in our project.
Great, thank you.
Thank you.
Okay, questions? Any questions? Have you two looked into whether there's actually soil data sets that you could have used, perhaps?
We did look into some soil data sets by contacting one of the companies here. I forgot their names, but they haven't responded back to us. Only like like 1 week ago, they contacted us, but at that point, we couldn't make the time.
It was too late. Yeah. Okay, but does that mean there are data sets that you could have used to validate your model?
The data sets they provided wasn't really much of use for us because it didn't have the parameters we were looking into.
Okay.
Yeah.
Okay, good to know. That's great. Thank you. Thank you again. Okay, we're right on time. Next up, Chelsea and Lauren. Sorry, Lauren. Who's gonna share the screen or the slides?
Hello, just give us one moment to share the slides
with you.
Sounds good. Yeah, sure.
I'm sorry about that. I'm going to be sharing my screen now.
Okay.
Great. Hi, my name is Chelsea Obede, and I'm a third year UTSA student majoring in computer science.
Hi, my name is Lauren Sande, and I'm a third year student majoring in business computer information systems. And our project is increasing accessibility and education of sanitary hygiene in Kenya.
Numerous Kenyan girls well into their puberty don't acquire adequate knowledge and understanding of menstrual health, a topic often revered as a taboo in a male-dominating society. This widespread and prevalent issue highlights the impact of insufficient menstrual sanitation and education on young girls in school.
The World Health Organization, United Nations Child's Fund, and many leading scholars define menstrual health as awareness, information, and self-confidence that women and girls have regarding menstrual ability.
Accessible sanitary dispensaries, clean and safe facilities, and supportive environments that allow women and girls to manage their periods without embarrassment not only improves menstrual health, but hygiene management. The matter of contention is providing sufficient access to sanitation and education for girls and women in Kenya.
Companies like ARI and Genesis Care are acting as the forefront, providing the much needed accessibility that is possible through the acquisition of sanitary dispensers. They recognize this issue as not a direct result of absence of sanitary products, but as ARI calls it, lack of beneficiary-centered accessibility.
However, a new concern is increasing awareness amongst girls and women of where to locate and access these dispensers. Another concern is destigmatizing menstrual health among school administrators and workplace authorities in order to spread awareness of the need for more dispensers in public facilities. How can we then combat the lack of accessibility to sanitary dispensers, specifically in schools and workplaces where they are often absent?
Women and adolescent girls are challenged by negative attitudes towards menstruation and lower work and school attendance due to inability to manage menstruation. These challenges may be exacerbated by insufficient access to sanitary products, education, and discussion.
A study conducted in Nepal and Kenya showed the importance of the acquisition of good menstrual health in the workplace, noting the increased number of female employees once menstrual health actions and interventions were put into place. The study also noted the significance of menstrual health knowledge and education, describing how both female and male employees expressed the enhanced knowledge on physiology.
Young girls in schools also have reported to respond similarly to tactics such as the above. Many reasons cited in various articles and papers named to adequate nature of menstrual hygiene education amongst young girls and amongst young schoolgirls can cause many to develop shame and can attribute to the stigmatization of menstruation. However, providing accurate and extensive education with the addition of sanitation products can broaden one's knowledge.
A study conducted in Kilifi County in Kenya was put into place to link the correlation between the acquisition of menstrual health and student attendance. 140 schools were included in the study, where 35 schools each were assigned a specific program that broke down and tackled each individual aspect of menstrual health, such as providing standard government supply pads and health education, regularly supply pads monthly, and administer sex education monthly as well.
Although the research conducted did not show much results on the significance of mental health on attendance, it did, however, record the positive impact on students, noting how most felt positively about menstruation and their reproductive health, as well as understanding the importance of equipping ethical gender norms. And this provided support in the area, which was very beneficial.
As far as our application for this project, we decided to create a progressive web app. The main goal of this application is to increase the accessibility of sanitary products as well as provide menstrual health educations for girls and women in Kenya.
We have outlined specific requirements, features, and functionalities for the application so far, which has been some of our progress. We've also been able to gather information on the dispensary locations in Kenya, and we have been coding the front end and the back end.
We have also been able to include a Find Your Nearest Dispenser map feature. We're implementing geolocation by inputting the user's latitude and longitude to find the dispenser nearest to them. Additionally, we've done most of the front-end development, implementing initial user interface based on mockups.
Our next steps is to begin coding the educational aspect of the application. We will also continue to develop the front end and lastly connect the front end to the back end service.
The problems we could possibly run into are finding the accurate dispensary locations, time constraints again, which is just help creating and then fixing the potential bugs, making the transition smooth for the user as well.
Overall, our goal is for all young girls and women in Kenya to have better accessibility to sanitary dispensers. We hope to ensure proper education through our app, improving overall menstrual hygiene management one step at a time.
With the help of languages such as HTML, CSS, and JavaScript, as well as Flask, we were able to make and implement these features into our app, which is just the geolocation as well as the look of it. And this is what our mockup is.
Yes, so here's our mockup, and it is called Girl Guide because it helps as a guide for the women and girls for their menstrual management. And then here it says, find your nearest dispenser. They can input their location. And then here's the main page where once they input their location, they could see the nearest dispensers closest to them, and they'll be able to have access to it. And then also there's like a tutorial for them and some education for their menstrual management. All right, we want to thank you all so much for listening.
We also really want to thank Genesis Care as well as Ari as well for providing us with all the information that to help with the dispenser locations. Thank you.
Thank you. Questions? Is there a way for folks or institutions to submit dispenser locations, or is that your job to go out and find that information?
Yeah, so we wanted to add a feature that allowed the user to also input dispenser locations if they were to come across any.
Okay. Yeah, that would be interesting. They could just tag it and input it. Okay. And I was wondering, this depends obviously on the use of cell phones. What's the percentage of girls who actually has cell phones?
We don't particularly have the exact percentage, but we do know it's the majority, at least in the urban areas, have cell phones.
Okay.
And would think probably approximately like 50 or 40% in the rural areas that have cell phones.
Okay. Okay, so that's pretty high. Yeah. Yeah. Good. Great. Any other questions? Good. Thank you so much. Next up, we have Rajan and Karshan and Yash.
Yep, we're here. Kashan's going to share screen. I mean, Yash.
Okay.
All right, calm me down.
All right, we can see something.
Just 1 second. I don't know why the size is so small on this. Is it fine now?
It's better, yeah. It's good enough, yeah.
Okay. Yeah. 3, 2, 1.
Pneumonia is a leading cause of death globally. It inflames the air sacs in the lungs, which can fill with fluid or pus, making breathing difficult. Early and accurate diagnosis is crucial to saving lives, but the current diagnostic process can be challenging. Lung x-rays are a key tool in diagnosing pneumonia by providing visual evidence of the infection's impact on the lungs. But interpreting these images requires lots of expertise due to the very subtle differences between regular and infected lungs. The demand for radiology services is very high, but the availability of radiologist specialists is relatively lower. Therefore, non-specialists often end up having to interpret x-rays, potentially leading to inaccuracies. Deep learning offers a solution. By training convolutional neural networks on large datasets of lung X-ray images, we can provide a tool to support medical professionals in pneumonia diagnosis. The introduction of UNet and generative adversarial networks have revolutionized the field and biomedical image segmentation. However, challenges remain. Many studies achieve high accuracy on small datasets or are not easily reproducible, with many lacking generalizability. Our work focuses on using a pre-trained CNN on a large and public dataset to provide general and accurate assessments, while also providing insight into the model's decision-making. By improving the process of pneumonia diagnosis, we can enhance patient outcomes and support healthcare systems. We can also work towards a future where we wouldn't need professionals for assessments of X-ray images. Everything would be autonomous.
We started by diving into existing literature and models used for pneumonia detection. After thorough research, we found several promising CNN models to try, including ResNet 50, ResNet 34, VGG 16, and Hugging Face. Our goal was to identify models that would provide the best accuracy. Next, we focused on cleaning our data set. We removed images with incorrect segmentation to ensure our model trains on the most accurate data. This left us with the refined images of 165,000 X-rays, which we could confidently use for training and testing. With clean data in hand, we moved on to processing. This step involved resizing images, normalizing pixel values, and applying data augmentation techniques like rotations, flips, and zooms. These augmentations help us generalize better by stimulating a variety of real-world scenarios. We then organize our data set into training, validation, and test sets. The training set is used to train the model. The validation set helps tune hyperparameters, and the test set evaluates the model's final performance. This careful sorting ensures that our model performance is measured accurately and fairly. To fine-tune our model, we created a smaller subset of the data. This allowed us to experiment with different learning rates and understand concepts like valley and slice and learning rate curves. By identifying the optimal learning rates, we could train our model more effectively. To prevent overfitting, we implemented early stopping in our training process. This technique monitors the model's performance on the validation set and stops training when improvements plateau, showing that our model doesn't just memorize the training data, but generalizes well with the new data.
We trained a ResNet 50 model on a small subset of our dataset with about 2,160 images split evenly into train, test, and validation sets to optimize high accuracy. We first determined the optimal learning rate without fine-tuning, comparing learning rates at different points, and found that valley rate offered worse accuracy but less time per epoch. Without fine-tuning, we achieved an accuracy rate of about 53%. When fine-tuning, early stopping halted the process at about 7 epochs, with no improvement post the third epoch. We optimized our ResNet 50 model by unfreezing it and adjusting the learning rate, and the model was fine-tuned for 10 epochs with no improvement after epoch 2. Loss trends in learning curve graph present good generalization, and we got an accuracy of about 59%, a 6% improvement due to fine-tuning. We ran the model on the full data set of about 35,000 images and found that each epoch took about 2 hours to complete, and hence we reduced the number of epochs for the initial training to 2 epochs and only got to fine-tune for 1 epoch and had to remove any further fine-tuning cells. We found strong negative correlation on the learning curve indicating that the model was generalizing very well and that we would have achieved much better results if we were able to fine-tune the model as we did on the smaller data set. Our test accuracy was about 57%. The model accuracy focuses on the pneumonia fluid or pus buildup in the left lung, as can be seen in the GradCam heat map that is seen, and it points out areas and images that contribute most to the prediction made by the CNN. We believe that our accuracy was affected deeply by the errors in these segmentation images. As you can see, our ideal data set, which we tried to obtain through pre-processing, can be seen on the left. However, many of the images in the data set complete incomplete segmentations. Thank you.
Awesome, thank you. Questions? Questions from the audience? You said 57% accuracy. Do you know how that compares to state of the art, but also to humans?
Yeah.
Yeah, go ahead.
Yeah, so when we were doing our research, the research paper we found from Mimic had about 70% accuracy, and with the smaller data set, we were getting about 57 to 60% accuracy. So we were within like a decent range.
An important thing to note here is that the research that we found was with, like, they essentially used a slightly different data set in which there were no segmentations. So the quality of the images was higher, and the size of the data set was much larger. So we weren't able to use that.
Okay.
Actually, the research papers that we saw, most of them use about 5,000 to 6,000 images only, and they reported much higher accuracy than what we got. We also did try on a 5,000 data set, 5,000 image data set, and we got like 97% accuracy, but that was due to overfitting. The data set was not big enough.
Yeah, I see. Yeah. Okay, 97 is pretty good. Yeah. Good. Okay, great. Thank you again. Moving on to Sanjana and Ronit.
Yeah, I'll be sharing my screen in a second.
Sounds good. Okay.
Okay, so our project is personalized mathematics learning. I'm Sanjana, my partner is Ronit, and our contact information is on the screen. And we are both from the University of Illinois at Urbana-Champaign. So the goal of our project is to provide learners of all backgrounds, whether they are behind or have a learning impediment, a unique pathway to learning through a series of questions that build towards a desired learning outcome through a web interface. And how do we plan to achieve this? It's as simple as asking a list of questions. But our project is a bit more complex than that. It really is an adaptive learning system that takes into account the learner's background knowledge, as well as factoring in the current motivation and comfort level, adjusting the questions asked accordingly. So this is more what our system looks like. The reason behind our project is that we want to create a learning tool that changes according to the learner's mindset and performance, allowing them to answer less questions and learn more efficiently. And existing studies have talked about the significance of personalization as seen on the slide. Taking a look at how our project works, the learning system is essentially a bunch of connected graphs where each node in the graphs represents a question to ask the user, and each node contains the question itself as well as the topic of the question, as you can see in the diagram.
Our project uses 3 different models: the expert graph, the learner graph, and the tutor model. The expert and learner models store information about the question, answers, and learner stats, while the tutor model is responsible for choosing the next appropriate question to ask the user. The expert graph consists of nodes, which represents the questions, as said earlier, and the edges connecting the nodes, which represent prerequisite skills for the questions. The graphs can be made manually by experts or generated through an algorithm, which is what we have done. The next model is the learner graph, which is identical to the expert graph in terms of how it's structured, but it stores the probability of the user answering the question at each node based on the topic. This information is unique to each learner. So the tutor model is not a graph, but an algorithm that's tied to the graph that uses data from the learner model, learner performance, mood, and mindset heuristics to most efficiently choose the next question to ask the learner. Essentially, it's the brain of the system. There are a handful of adaptive learning systems out there that focus on more than just a learner's performance. An example of work like this is that uses the student's typical time to complete to measure their concentration. Our work, in contrast, focuses on the motivation. In order to obtain data to help generate the math questions, we use the Google DeepMind math dataset. This dataset, given the topic, generates a random math problem with an answer. Unlike traditional datasets, the size of the graph we can generate is what we want it to be. Going more into depth into the generation of the expert graph, a skill tree is used to help generate the graph. As you can see, the skill tree connects the topics based on their progression. That is addition coming before multiplication, as seen in the graph here. The expert graph, which is that really complex graph on this side, can contain hundreds of questions. Each is connected in accordance with the skill tree. For each question, the answer choices are randomly generated by adjusting the numbers. Now for the algorithm. The learner graph's probability for each topic changes according to item response theory, a mathematical model that uses a sigmoid graph to map the relative skill of a learner with the probability they'll get the question of the certain topic right. For the graph traversal, we use A* to reach the nodes with the learner's goal skills, and the heuristic used prioritizes nodes with skills closer to the goal. Edge weights or viability score are updated after every question, showing the viability of traversing adjacent nodes using performance and mindset data.
So this is what the application actually looks like. The user is first asked what their previous skills are and what their goal skill is from a list of skills based on the data used to generate the questions in our system. And we use Streamlit as our main front-end tool due to its efficiency and various features. Then the actual math questions are generated, and the layout is as shown, where the question is at the top, followed by the answer choices, and at the bottom is a graph with adjustable sliders for the user to input their current motivation and comfort levels prior to answering the question. We hope that our project can serve as a beneficial, interactive, and positive learning tool in math, which can be used at any time by all kinds of students worldwide, no matter what conditions or stage of knowledge they have, thus making digital education more powerful and closer to the experience of one-on-one in-person instruction. Some challenges we encountered included determining when the learner has achieved content mastery, which is especially hard to gauge without having people to test, and also the fact that we weren't really accounting for all the potential indicators that could affect learning, like time spent on the questions. Our next steps are to test the application graph traversal algorithm for effectiveness and functionality, and potentially continue to enhance the interface along the way as we test and receive feedback from other subjects. And that's all. We hope you enjoyed our project. We would like to thank the altREU program for supporting our work, and we are open to any questions or suggestions. Thank you.
Thank you. As always, questions? Any question from the audience? So you've answered the validation question. That seems that's not quite done yet, right? You probably tried it on yourself, but you haven't done a more comprehensive test with subjects. Is that right?
Yeah.
Okay. And I was wondering too, so you, what happens if you fail the test multiple times or a subject doesn't actually know the answer? What's your algorithm doing? Is it going back?
Essentially, yeah. So like it can go back, and every time it goes to a certain node, it like generates a new question of the same topic. So the user doesn't do the exact same question, but they do a slightly different variant to eventually gain.
Oh, but is it going to be an easier question or of the same level?
It should, like probably around the same level.
Same level, okay. Okay, I wonder if, at some point you kind of have to give up and go back a level when you realize the user just can't do that level yet, right? But
Yeah,
that
that's
doesn't.
probably like how the graph algorithm would work.
Yeah.
If that situation did occur.
Okay. Okay. Good. Well, thank you. Thank you, Jen. Next up, we have Srijan and Jason.
Yeah, I'm here.
Okay.
I'll share my screen. Oh, wait. Okay, can you see?
Yeah.
All right. All right, we're gonna get started. All right. All right. So, hi, I'm Srijan, and with my partner Jason, we built our project Run Tempo, a dynamic music system based on exercise and running cadence for an enhanced running experience. So let's look at the statistics of running. Running is one of the most popular forms of exercise in the world. According to a 2021 study by World Athletics, 40% of surveyed people consider themselves to be runners. And in the US, 50 million people run or jog. Observing the relationship between music and running, studies show that music increases endurance, elevates heart rate, and overall improves the running experience. However, if we look at the tempo of music, we see a positive relationship between the tempo of the music and the cadence of the runner's steps, which means that runners adapt their pace to the music they hear. So it's widely known between runners and researchers that runners prefer music at a constant tempo to synchronize their steps to. But the problem with existing solutions is that the tempo range is too large and the recommendation system is not dynamic. So lots of runners just give up with music and don't listen to music while running. Our solution is to combine accelerometer data and step count or cadence in order to properly generate an ideal tempo range for the user and cue songs in that tempo range with the user's personal music preferences. So how are we getting this data? Apple and Android actually have very useful tools already built in that are available for use. This includes the Core Motion library as well as Android Health. Since these generate cadences, we are able to apply basic filters to generate an accurate cadence BPM for the user. We also use Spotify's SDKs. With this data, we can use Spotify's SDKs for iOS and Android to allow our app to do basic things such as play and connect to Spotify and make API calls. So an important part is authorization. So in order to allow our app to actually access Spotify's more advanced features, we first had to authorize the app by using access tokens, which we sent through the web API, allowing us to send and request information.
After allowing our app to access the web API endpoint, we are able to access Spotify's web database to generate recommendations as well as retrieve more information that we aren't able to get with using the SDKs. The UI is able to display basic information during the user's workout, such as like steps per minute, song information, such as author, tempo, and duration. Additionally, we have a settings page where the user can choose options to tempo match. They can set their tempo. They can also choose their music preferences. So to put it all together, with our accurate steps and cadence, we are able to make requests to the API that returns songs with the same tempo. The app is then able to cue the song and display the correct information on the UI. Some difficulties we had when creating this were that the same songs are being recommended, which we had to fix with like seeds and random selection. Additionally, API denials were pretty frequent, and we fixed that with fresh token generation. In the future, we still have to publish this app on the App Store and Google Play Store, and we need to update the GitHub for public release, as well as test and get feedback from users, as well as like add new features. To conclude, we created an app that connects running and exercise with music tempo, and we hope that this app will encourage people to exercise and run more, which will help raise overall public health.
And that's our presentation.
Great. Thank you. Questions? I would definitely like to try this app. So hopefully you guys get to put it on the App Store. I remember we talked about some patents that we found. Did you more carefully look at whether somebody else has done something similar?
Yeah, we actually saw that Spotify actually used to do something similar,
Really?
but then they discontinued it. And we did some research. It seems that they discontinued it because of server costs and just like cost cutting. So
Interesting. Yeah.
yeah.
Okay. So, but there was a need perhaps or a market for that. Yeah, that's interesting.
Yeah.
Good. And the API limitations, that's a matter of money. If you pay enough, you can get as many requests as you'd like. Is that correct?
Yeah.
Okay. Great. Thank you so much.
All right, thank you.
All right, moving on to our biggest teams, Sumaya, Selena, Sonika, and Sahana.
Yeah, let me just share my screen.
Okay.
Sorry, one second. Okay.
That's
So,
good.
yeah, a 2023 survey by the University of Chicago's Urban Labs found that 67% of Chicago residents feel unsafe in their neighborhoods. And this was our driving factor for our project, Predictive Crime Analysis.
Hello, my name is Selena Anwar, and I'm a CS major.
Hi, my name is Sonika Thamarasan, and I'm a computer science and economics major.
Hi, my name is Sahana, and I'm a computer science and statistics major.
And my name is Smaya Farouk, and I'm a computer science and crop science major.
Our project aims to enhance community safety in Chicago by predicting the probability of crimes at specific locations using the LSTM and random forest model. We also created an interactive website for users to forecast potential crimes. So we're first going to discuss our data collection and cleaning process, and then we'll go through the two methodologies we use in implementing our models, and then we'll dive into our results and accuracy scores, and finally, we'll discuss how we applied our findings. So to collect data for this project, we used the Chicago Data Portal, which is a reliable source that provides frequently updated crime records. The same data set used differently was used to create a heat map to address potential biases. So we cleaned our data using Python libraries like pandas to remove irrelevant data and null rows. So the initial data set had 22 columns, but we took this down to 4. So it included crime type, location, and date time. And then we split the date column for model input.
The random forest model is a model that relies on multiple decision trees and then combines their output to come to one decision. And they're known for their ability to reduce overfitting due to the randomness in each tree. And this is one of the methods that we decided to use.
The second method we used was a long short-term memory model, and this is a type of recurrent neural network, and it's capable of learning long-term dependencies. And LSTMs are particularly effective for time series prediction and NLP tasks due to their ability to retain information.
The data for the random forest model was split into training and testing sets of 67% and 33%, with the set random state so that the findings could be reproduced, and then ordinal encoders were applied to preserve inherent ordering. While creating the random forest model, we found that 100 decision trees with a max depth of 25 led to the highest accuracy scores. The data was also trained in parts, alleviating runtime issues, which we had dealt with previously. And then the F1 scores from the table suggest that many of the crime types were unable to be accurately predicted. This is likely due to the fact that some crime types are inherently less common than others, leading to less data and less accurate predictions overall.
For the LSTM model, the data is split into training and testing sets, with 80% for training and 20% for testing, ensuring reproducibility with a fixed random state. And the resulting data sets are then converted into NumPy arrays for compatibility. And in total, 6 layers were used, and within each layer, 100 neurons were used, and we had a dropout rate of 20% to prevent overfitting. And to help with efficiency, we also reduced the batch size to 128, and an epoch of 10 were also used. And the graph here shows that while the training loss decreases and stabilizes, the test loss fluctuates, suggesting potential overfitting. And this indicates the model performs well on training data, but struggles to generalize to unseen data. And in the end, our random forest model had an accuracy of 17%, whereas our LSTM model had an accuracy of 21%. And we believe the low percentage is due to changing trends in crime, as well as issues in the model architecture.
So we also created a Flask-based web application, also using HTML, CSS, and JavaScript, and it uses a Google Maps API to retrieve user location as an input for the pre-trained LSTM model and outputs the top 5 predictive crime probabilities. So here's a quick glimpse. On the left, you'll see the homepage that shows the map and location and top 5 predicted crimes. And then on the right is a heat map that I will go a little bit more into on the next slide. So we included this heat map of Chicago that offers insight into crime patterns, but also highlights the complex implication of predictive policing. So it's by race. So, and we acknowledge and show on our website and explain that how these predictive modelings can perpetuate systematic biases. So our next steps would be improving our accuracy from 20% and maybe try using an XGBoost model, which research suggests might be more accurate than LSTM and random forest, and finally deploying. So thank you to the altREU program, and we are free to take any questions.
Excellent, thank you. Questions? We had some discussions in our previous meetings about privacy concerns and concerns about people concluding the wrong things, perhaps. What did you end up doing, or how did you address those things?
Yeah, so although our website isn't deployed yet, we do have a lot of like cautionary aspects when we show the top 5 crime probabilities in like bright red. It talks about the inaccuracy of the model. And then that's also why we decided to include the heat map as well. So the heat map is of arrests in Chicago by race. And then we have a description that talks about how predictive modeling can be dangerous for increased policing in certain minority neighborhoods. So we ended up making our website a lot more awareness-based rather than straight up like predictions.
Okay. Okay, good. Yeah, that's quite sensitive data and predictions that you're making here. Yeah, that can really influence people's behaviors, and where do you buy the house, where do you go to school, things like that, right? Good. I'm glad you took these concerns to your hearts. Great. Thank you. All right. Let's move on to Sophia and Ishida. We can see you, but you're muted.
Oh, okay. Can you see our screen?
Yep.
Okay.
Coming up, yeah. Good. Looks good, yeah.
Okay.
Perfect.
So Phoenix is no stranger to extreme climate. Widely considered as the hottest city in the US, the city's summer temperature spills over 100 degrees on a regular basis. And then one Science American article describes the effects of Phoenix's heat, states that it was a 2023 hit of record-breaking 645 related heat deaths.
So Phoenix suffers from what scientists have dubbed the urban heat effect due to rapid industrialization and population growth. And this effect occurs when cities absorb and retain heat during the day due to materials like cement and asphalt.
Urban heat islands lead to higher energy consumption in the form of air conditioning, health complications, worsening air quality, drought, and much more potential consequences. Tackling urban heat through infrastructure can lead to a more green, eco-friendly environment, making Phoenix a more livable, less hostile experience.
And in the face of such extreme climate, Phoenix and Maricopa County have made significant infrastructure efforts to combat the heat and thus make their region more livable. But the question is, how will the urban planners of Phoenix determine which infrastructure works best where?
Hello, we are Sophie Vargas and Ishita Deshpande, and our project Sun Maps was created to target this specific question. We are both incoming sophomores at Arizona State University, and we both have experienced just how hard it is to really get around in the Phoenix heat.
So to determine what infrastructure should go where, we developed an algorithm that had inputs of urban zoning, local climate zoning types, and mean radiant temperature. And then based on these inputs, our algorithm would output 5 different infrastructure solutions along with their projected temperature reductions.
Our urban zoning type dataset consists of 8 zones: commercial, industrial, single-family residential, multifamily residential, planned unit development, downtown code, county, and non-developable. We combine this into the general categories of commercial, industrial, and residential.
Our local climate zoning data was provided by a research paper from Arizona State University's heat resilience team. And there are 14 different climate zones in total, and they're categorized based on factors like concrete and pavement, building heights, construction materials, and vegetation height.
Our MRT mean radiant temperature data set was provided by the same ASU heat resilience research team, and mean radiant data temperatures are calculated from the factors of surrounding walls and surfaces and their positions with respect to those surfaces.
And with this combination of parameters, we used a series of if-else statements to determine the capacity at which each infrastructure type would be used. And so we have 5 different types of infrastructure: artificial shade, tree canopy, cool roofs, reflective pavement, and water misters.
Utilizing the information we had gathered from research articles, then we wrote our algorithm using conditional logic. So on the left is our if-else statements, and these were based on research. An example of that is that cooling potential was added to street trees is greater in lower density residential neighborhoods.
And then we also generated the distributions of temperature values for each local climate zone. And then we used the mean of each climate zone in our function. So for example, if the input temperature was higher than the mean, then we would suggest something like a higher increase in tree canopy percentage.
To apply our algorithm, we created a user interface that consists of an interactive map of Phoenix, and then users are able to navigate through the map and then choose a visual overlay of LCZs, MRT, and zoning types, and then take away those zoning types if necessary.
And then the user can click on a location in the map, and then it'll show a pop-up of the location's coordinates, and then the accompanying side menu will display the location's climate zone, urban zoning type, and mean radiant temperature, and then a list of solutions to use and its projected temperature reduction.
So our project is mainly geared towards those who are implementing cooling infrastructure, namely urban planners and the city government. So rather than having urban planners look at zoning, heat, and climate research separately, our application would provide easier insight and access into what would actually work best in order to reduce and make heat mitigation possible.
And by having a clear understanding of which certain infrastructure changes will actually help with heat mitigation, Phoenix Metro can take greater steps towards tailoring their urban planning for the nuanced and individual needs of their communities, providing tangible benefits that can be communicated.
However, we can also hope that it would be used as a general awareness tool for all of the residents in Phoenix who would want to know how they could actually combat the heat. Having residents generate attention about what they would want to have in their local communities would help these changes actually get implemented rather than just be suggested.
So for our next steps, we're planning to integrate machine learning into our decision algorithm. And then we would also like to integrate cost as a factor, whether it be sorting the list of solutions by cost or just filtering out the most expensive solutions out to begin with.
So finally, we would like to see how our model could change if instead of a list of separate infrastructure solutions, we provided a solution that combined different infrastructures for the largest total temperature reduction. So we would want to recommend a combination of infrastructure instead of all of these infrastructure solutions separately.
And that was all. Thank you for listening to our presentation, and we hope you learned a little more about cooling and urban heat.
Thank you. Questions? So trees isn't really a thing in Phoenix, right? That was not part of your cooling strategy, is that correct? Yeah.
Oh, it was, but like the research we were looking at like determine what type of trees. So like non-native trees that had like more lush, like thicker leaves would provide different types of like shading results than like a palm tree or a cactus.
Yeah. Okay. Yeah, interestingly, I was just reading an article about the fact that trees help, but they need to be in the right place. And I always thought, well, shade is good no matter what, but apparently that's not the case. You can place the trees in the wrong place and it would actually increase the heat if you do it wrong. So that I thought that was interesting. And that could be an extension of your algorithm. I was also wondering how you could expand it to other cities potentially. Your approach, how would it generalize to other cities?
Well, when we were presenting and then Dr. Barmasi was suggesting how we could expand it, he was saying we could, rather than like expanding it to like, say the state of Arizona, we would just target similar cities with like similar climates like Las Vegas or Albuquerque.
Yeah. Okay, good. Great. Excellent. Thank you. All right, moving on to Alan and Alex. Thank you.
Okay. All right, counting us down. Oops. Ready?
Yep.
Ready.
All right, so our project is called Health Helper Chatbot for residents of King County. I'm Alex Ho, my partner is Alan Chan. We're both seniors at Oregon State University. All right, due to the pandemic in recent years, there's been an increase in mental health issues leading to an increase in demand that mental health service providers are unable to meet. According to the APA, since the beginning of the pandemic, every year practitioners have noticed an increase in patients with mental health disorders, which is a trend that will likely continue as an awareness is being spread of mental health issues and seeking help becomes less stigmatized. And as lockdown becomes less strict through the recent years, there are more patients being seen in person as opposed to strictly remotely. But people may not be fully aware of the services that mental health providers have and are not aware of the options that are available to them, which is why we wanted to create a chatbot that will help users find resources in their area that they can utilize and figure out the one that suits them best. We primarily wanted to focus our project on the King County area, since that's where both Al and I are from, and we're both residents in Seattle. We looked for information about mental health service providers in this area and different services that are provided by them. The main data set that we ended up using came from this King County mental health and substance use disorder provider, and it contains information on King County contracted providers with information including the clinic's phone numbers, their addresses, and the neighborhood. We then processed the CSV data that we got from the website, turned it into JSON format, and we use this to train the chatbot on how to use this information when generating its responses for user queries. And this is our current Flask app. This is the front end that we have set up. At the bottom right, there's a icon that users can click, and it'll pop up a chat window that they can then interact with the chatbot. And here's an example that we have of an example query that a user may have, where the user asks about service providers, and then the bot provides back information about the address, the phone number, and prompts the user for additional help.
To reiterate, our project leverages OpenAI to develop the logic behind the chatbot. We used Flask as our backend to create a web application styled with HTML and CSS. The most important API we are using is called Assistant API, which allows us to call functions to build a chatbot using the OpenAI LLM. By using the assistant, you can assign instructions, leverage models, and use files to respond to user queries. So how the chatbot works is that the process to get a response back to the user and get displayed gets broken down to three components: the chatbot running the assistant, the thread, and the run. You know about the assistant, but to explain the thread, it is basically a conversation between the assistant and user. The thread is used to store messages that are used to control the assistant's conversations. And the run is explained as the way in which the assistant uses its configuration and the thread's messages to perform tasks by calling models and tools. As part of a run, the assistant appends messages to the threads. Going through a run through to visualize how this whole process works with our bot. Step one is requesting the user input through the assistant from the interface of our web application. We ask the user what neighborhood they're specifically from for curated responses. After which the messages will then be stored. The messages will be stored in a thread created from function calling. The thread stores and deletes all messages when the users exit. And once there are user inputs, it's ready to run. When the messages are at the run phase, the LLM model references our datasets when necessary to formulate a response. In our case, personalized healthcare information that gets sent back as messages to the thread. Once we have our response message, through function calling, we take that response generated and send it to the chatbot to be displayed. The chatbot then asks again if there is anything they can help with, and the cycle repeats itself. For our future considerations, we thought about expanding our datasets by calling in and requesting local health and mental health facilities for any networks that they might have, and having a more thorough data set that categorizes what type of service each facility provides to be more precise for our users. Thank you so much for listening in.
Thank you. Questions? Did you consider implementing something like a follow-up where you have a user, they ask for help, you get them the resources that, or your chatbot provides the resources, but then you don't really know whether that person actually uses these resources. So what if you would implement some sort of callback, I don't know what the right name would be, right? Where after a day or two, you're sending them a little message and asking hey, how is it going?
Yeah, we thought about that actually. We thought about having surveys as part of our web application, so that we can get data from the user, if our chatbot is too hard to interact with, if there's any glitches or hallucinations to get.
Yeah.
Another issue I think that we discussed during one of our weekly meetings with that was we didn't want to be storing our patients' information, especially if it's an insecure way.
Yeah.
And that would affect certain legal issues regarding that as well.
That's a very good point. Yeah, there's definitely privacy issues. Yeah, good. I mean, it could just be the email, but still, or a phone number, but still, it's personal information, and that's always, tricky, or makes things trickier. Great. Good, thank you. We have one last presentation by Daniel.
Awesome. Right on. Hello.
Cool. Yeah.
Okay. Awesome. I appreciate the opportunity to present with everyone today. My name is My name is Daniel Monahan. My partner is Holden Lee. Unfortunately, he won't be able to join us today, but we're talking about online learning and specifically deep reinforcement learning and spiking neural networks today. Let me actually make sure this is playing correctly. Awesome. So the background here is that AI compute needs are doubling every 3.4 months. So there's this exponential increase, which is outpacing Moore's law, and the reason this is an issue is that it sort of runs into limitations, and becomes very expensive. So you can see something, a model like ImageNet, this estimate of economic costs is, order of 75, order of magnitude 75, and greater CO2 emissions. And our options here are to improve compute efficiency. And so what we're exploring is, there's power efficient hardware. We've seen mem capacitors and memristors and novel architectures such as non-Voigtman machines and efficient algorithms reduce computation expenses. So one option here is we've been exploring is spiking neural networks, which essentially use biologically inspired event-driven processing to perform operations like analogous to artificial neural networks. And these are most often built up with integrate and fire neurons, which some input spikes, and once they reach the potential, they limit their own output spike here. So in order to use these networks, we have to take our inputs and we will decode them and encode them into spike trains here. So once these enter the network, they're propagated through, and then we'll get these output spike signals, and we'll have to decode those. And in our case, we're using whichever neuron essentially spikes the most or at the highest frequency. We take that to be our predicted output or best course of action for an action network. So we're using this learning rule. It's biologically based, spike timing dependent plasticity. If a presynaptic neuron fires before a post, then we actually increase the weight of that synapse. And likewise, or conversely, if a postsynaptic neuron fires and it's not triggered by a presynaptic neuron spike, then we will weaken or decay that synaptic strength. This is something that's found in biology, and it's used as sort of an unsupervised learning rule. But it gives us this mechanism which we can formulate into, we've used this eligibility trace to track synaptic forward connections. And then we have this reward signal, which we use as our weight modulation. The reason that we're interested in SCDP is because we've seen an example of capacitor neural networks actually inherently carrying out these long-term potentiation and long-term depression or increasing synaptic weights, capacitor networks. So we needed a problem, and the problem we were attempting here is a Santa Fe problem. So this ant is supposed to basically forage through this trail, and it gets more sparse as it travels. And essentially, we came up with the credit assignment that if it sees a food particle, we give it a small reward. If it collects a food particle, we give it a larger reward. And if it's basically idling or looking around and not finding food, then we'll give it a negative dopamine reward here. And in order to memorize this trail, we wanted to use some sort of a current architecture. So because LSTMs are used for sequential processing, we sort of have this, spiking version of an LSTM. So here we have some results you can watch as this ant hopefully will load. Oh, well, let's see if we can get this to work. So yeah, you can see how he sort of runs around. Kind of, this is when it's being, it's sort of learning more behaviors, and they seem to sort of almost do this evolution over time. And you'll see in the next run here, he does just slightly better. And they sort of have adapted these behaviors where they will, most commonly, they will just pick, one direction to turn around, and eventually they will, when they see food, they will head forward. Otherwise, they will sort of randomly, travel around the map and look for a new trail. So this one actually manages to make the jump across this gap, sort of gets over here. But so issues we sort of ran into. It seems to not really like playing videos very much. Anyways, so issues we ran into is that performance became very volatile, as behaviors would be sort of incorrectly rewarded at times, And it was able to game some systems where it would basically just look at food over and over again. So we'd see this increase in performance, and then as training increases and it kind of gains momentum, it sort of starts to kind of forget its behavior. So options moving forward would be, we've seen sensitivity to initial conditions. So genetic algorithms might be interesting. You may need to increase the network size. Or interestingly, we've been thinking about doing agent-based approaches where the reward signal is modulated. But yeah, appreciate you all listening to me today, and I'm happy to answer any questions you may have.
Thank you. Questions? Can you say something about potential hardware implementations, perhaps? How is that related to what you're doing?
Absolutely, yeah. So we've been looking into specifically mem-capacitive networks, which mem-capacitors would be sort of they're like in this family of mem elements, or originally the memristor is the first mem element, but the benefits are that they have the property of storing some sort of memory state, as well as carrying out these neural network activities. And so it allows this kind of consolidation of memory and compute in one area, and at a greater power efficiency as well. Yeah.
Okay. Yeah. Excellent. Good. Any other questions? All right. If not, this wraps up our Summer Research Symposium. Congratulations to all the students. I was very impressed by their presentations. Awesome work, awesome preparation, awesome presentations. That was really cool. I will share the recording with everybody. I've already had requests from other folks who couldn't attend, who want to see the presentations. So I hope you learned a lot. I hope you took something home with you, something for your resume, something for your experience. Thanks again to all the mentors and all the supporters of these various programs that we supported over the summer. And I'm very excited to see the book being published in the next couple of weeks. If you haven't submitted your chapters yet, today is, I believe, the day. Yeah, all right. Thanks again for being here. Thanks again for presenting, and have a great end of the summer. Bye.
Thank you.